For 70 years, we cast our gaze across the cosmic ocean. We chased the ghosts of dying stars, mapped the very edge of observable reality, and sought answers in galaxies billions of light years away. But in our epic quest, we overlooked the obvious. A celestial neighbor waiting just beyond our doorstep, Alpha Centauri, a mere 4 light-years from Earth. Until now, it remained a mystery hidden in plain sight. Too close, too bright. Its 3 suns created a blinding glare, a celestial floodlight that drowned out any secrets it held. But the James Webb Space Telescope sees differently. It peers into the universe, not with visible light, but with heat, through the dust, through the glare, into the hidden heart of things. In December of 2023, Mission Control turned the great eye away from the distant cosmos and pointed it toward home, to our nearest stellar system. At a distance of 4.37 light-years, it is so close that a journey on foot, at 3 miles per hour, would take 80 million years. The first exposure lasted 14 hours. Scientists expected routine data, a sharper image, a confirmation of what was already known. What they received was an anomaly, a signature emerging from the habitable zone of the system's smallest star. It was clear, unmistakable, verified across 3 separate instruments. At the European Southern Observatory, Dr. Sarah Chen saw the transmission first. She ran the analysis twice, then a 3rd time. At 2 in the morning, she called her supervisor. "We have a problem," she said. The problem was not that the data was wrong. The problem was that it was right, and it made no sense. The signal blazed in the mid-infrared spectrum, wavelengths between 5 and 12 micrometers. This is the language of atmospheres. It tells of composition, of temperature, of the delicate chemistry that unfolds in the thin shell between a world's surface and the void. Webb had detected it all, in a fidelity no one thought possible. The planet, Proxima Centauri b, was not merely a rock orbiting in the zone of life. It was alive with process. It showed active atmospheric processing, temperature gradients, heat distribution patterns that could mean only one thing: weather, real weather, clouds forming, moving, and dissipating across a world that was not our own. It suggested a hydrological cycle. The discovery has forced a profound reevaluation. For generations, we looked to the farthest reaches of space for signs in the dark. We searched for a faint echo across an unimaginable abyss, never thinking to listen for a heartbeat in the room next door. Perhaps the universe is not as silent as we believed. Perhaps the greatest secrets are not hidden at the dawn of time, but have been waiting patiently, right in our own cosmic neighborhood, for the moment we finally learned how to see. It was found in the year 2016, not through a direct glimpse, but by listening to a whisper in the dark, a delicate, rhythmic tremor in the motion of the star Proxima Centauri, a wobble caused by the persistent, gravitational tug of an unseen world. From this cosmic shiver, scientists deduced the essentials: a mass 1.3 times that of Earth, orbiting its star every 11.2 days. It existed in the temperate zone, the hallowed ground where liquid water could pool on a planet's surface. But for years, it remained a ghost in the data, a world of pure potential. Its atmosphere, if it had one, was invisible, until now. New readings revealed something astonishing: a vertical atmospheric structure, different temperatures at different altitudes. On our own world, such a profile is the signature of a complex engine at work, of solar heating, the convection of gases, the transport of moisture, and the subtle dance of chemical reactions. To see this on Proxima b meant it was not merely a sterile rock adrift in the void. It was active, dynamic, a world alive in the geological sense. But as one veil was lifted, another, far more formidable, remained. In astronomy, brightness is a tyrant. The nearby Alpha Centauri system presented not one challenge but 3, a trinity of stars all blazing with an intensity that erases anything small and dim in their vicinity. Alpha Centauri a star that outshines our own sun by a factor of 1.5, burns across 25 trillion miles of space, yet remains a brilliant point of light in Earth's southern skies. Its companion, Alpha Centauri b, glows with nearly equal ferocity. For 80 years, they are locked in a celestial waltz, a gravitational embrace of overwhelming light. And then there is Proxima, the red dwarf. Smaller, dimmer, yet from our perspective, still bright enough to hide an Earth-sized world in its blinding halo. The Hubble Space Telescope turned its gaze there in 1995. The resulting images showed only two brilliant, bleeding blobs of light. No planets, no detail, just a torrent of photons overwhelming the sensors. The technology was simply not ready. It was the equivalent of aiming a camera directly into a pair of headlights and trying to discern the make of the car behind them. From the ground, the view was even worse. Our own atmosphere, the very air we breathe, conspired against the search. Heat rising from the Earth makes starlight tremble. Water vapor scatters the precious infrared signals. By the time the light from Alpha Centauri completed its journey, it was a fractured, smeared, and useless message. Adaptive optics offered a partial solution, using laser-guide stars to correct for the atmospheric wobble, sharpening the view. But they could not pierce the fundamental glare. The true breakthrough came from a device of profound elegance, the coronagraph. It creates an artificial eclipse, a perfect shadow cast inside the telescope itself, blocking the direct light of the star to reveal the faint worlds hiding at its edge. Early versions were imperfect. Light diffracted around the edges, leaking through, the glare always finding a way in. But instruments of exquisite precision. For years, scientists debated whether Alpha Centauri was even worth the effort. Telescope time is a finite and precious resource, with thousands of proposals competing for mere hours of observation. To point our greatest eye at the brightest, most challenging target in the sky was a gamble of historic proportions. It was a wager that, beyond the blinding light, something profound was waiting to be seen, forcing us to invent new ways not just to look, but to finally see. For generations, the great cosmic mysteries seemed to lie only in the unfathomable distance, in the hearts of remote galaxies, in the crushing silence of black holes. Why linger on the stars next door? Then, in the year 2022, the argument shifted. A world named Proxima b, orbiting our closest stellar neighbor, began to haunt our planetary models. Computer simulations hinted at the impossible, that it might cling to an atmosphere, a fragile shield against the fury of its parent star, a possibility, a whisper, a reason to look closer. The James Webb Space Telescope was given just 14 hours, one observation, one chance to get it right. The target was a ghost in a storm. Proxima Centauri is a red dwarf, a star prone to violent, world-sterilizing flares. But these stellar tempests have interludes of quiet. The Webb's operators waited and caught one of those fleeting windows of calm. The timing was perfect, the conditions pristine, the data revolutionary. Webb's infrared eye bypassed the limitations of the past. It sees the universe not in reflected light, but in warmth, the faint thermal glow of worlds themselves. A coronagraph, a mechanical thumb, blotted out the glare of the system's three suns. The sensors locked onto the cooler signatures hiding in the dark. And after decades of staring into a blinding light, we could finally see what lay hidden in our own cosmic backyard. It was not one planet, it was an entire system, more complex and defiant than anyone had dared to imagine. Three stars, bound together, should not host stable worlds. This was a foundational rule in the old texts of planetary science. Too much chaos, too many gravitational tides pulling in different directions, too much radiation from too many sources. Planets, we believed, required stability, a calm nursery, the slow, patient passage of time. The Alpha Centauri system offers none of these. The two main stars, A and B, whip around each other in a dramatic, elliptical dance. At their closest, they are separated by 11 astronomical units, roughly the distance from our Sun to Saturn. At their farthest, they stretch to 35 astronomical units, out to the cold domain of Pluto. This creates a gravitational environment in constant, violent flux, a zone where any aspiring world would be torn apart before it could form. And then there is Proxima, the distant third. It drifts 13,000 astronomical units from the central pair, a lonely outpost. Is it truly a member of this family, or a temporary passerby on a 500,000-year orbit. The uncertainty itself is a problem. When worlds are born, they coalesce from vast, swirling disks of gas and dust. Particles collide, they stick. Over millions of years, they grow. But this delicate process of accretion demands consistency, a stable gravitational field. In a system with 3 suns, 3 sources of gravity, 3 stellar winds, and 3 sources of heat, collisions become destructive. Instead of building, they shatter. The existence of this impossible system does not simply add a new chapter to our knowledge. It forces us to tear out the old pages and begin again, reminding us that the universe is not obligated to conform to our expectations, and that its most profound secrets may not lie in the deepest dark, but in the light just next door. It was a place of cosmic violence, a gravitational battlefield where 3 suns danced a chaotic waltz. Computer models, born in the 2000s, were clear. No world could survive here. Any fledgling planet would be torn apart, scattered into the void before it could ever draw breath. And then, in 2016, a faint, rhythmic wobble betrayed a secret. A ghost in the machine, a planet, confirmed. At 1.3 times the mass of Earth, it orbited squarely in the habitable zone. The discovery sent a shockwave through astrophysics, a single, impossible world that demanded a new story. If one planet could endure, perhaps others could as well. Perhaps what we saw as chaos was merely a more complex form of order, one we had yet to comprehend. The answer came from the unblinking eye of the James Webb Space Telescope. Its infrared gaze pierced the veil, revealing the system's hidden history. The 3 stars were born together, but Proxima drifted away early in their shared infancy, carving out a realm of its own. In the cosmic nursery, the siblings had separated, giving each star a sovereign territory to raise a family of worlds. But isolation is a relative term. Every 79.9 years, the 2 central suns, Alpha Centauri A and B, perform a close pass. Their immense gravity sends ripples through the system, not a cataclysm, but a steady cosmic pulse, a tide that clears away the unstable, making planet formation a perilous endeavor. Yet within this turbulence, there are havens, stable zones, gravitational safe harbors where a world might cling to existence. Webb saw them as patterns in the dust, thermal signatures revealing where matter could gather and where it was swept clean. An elegant, brutal order. For every world that found sanctuary, untold dozens were likely cast out, condemned to wander the interstellar dark. The lucky survivors hold the greatest secrets. 1.3 times the mass of Earth, a mere 7.5 million kilometers from its star, a year that lasts just 11.2 days. These are not merely numbers on a chart, they are the coordinates of hope. For this world, Proxima b, orbits within the hallowed ground known as the habitable zone, the narrow band where liquid water could exist. But its star is a red dwarf, a faint ember compared to our own sun. With a surface temperature of just 3,000 Kelvin, warmth is a precious commodity. To survive, Proxima b must huddle freezing night. This proximity comes at a cost. The star's immense gravity has seized the planet in a tidal lock. One hemisphere is trapped in perpetual daylight, scorched by an unblinking sun. The other is frozen in an eternal night. It is a fundamental law of celestial mechanics, seen across the cosmos, from our own moon to the planet Mercury. Draw too close to a greater mass, and the dance of rotation ceases. The tides always win. This world of extremes forces us to confront our most basic assumptions. Could life thrive on the Terminator, the twilight zone between fire and ice? Is a locked world a dead world, or simply a different kind of living one? The discovery of an impossible planet did not provide answers. It only deepened the mystery, reminding us that in the grand cosmic theater, the rules we thought we understood are merely the opening lines of a much larger play. For a planet trapped in a gravitational embrace, one side is scorched by an eternal sun, the other locked in a perpetual, crystalline night. The question has long haunted astronomers. Could life find a foothold in such a world of extremes? For decades, the answer lay hidden within the silent logic of computer models. They suggested a solution, a great equalizer, an atmosphere. If thick enough, it could become a planetary circulatory system. Winds, born in the blistering heat of the dayside, could carry warmth into the frozen dark. Ocean currents could distribute thermal energy across the globe. The world did not need to spin, it needed to breathe. Then, the James Webb Space Telescope turned its golden eye toward a nearby world, and the theory was put to the test. The readings that came back were astonishing. The planet's dayside registered a temperature near 300 Kelvin, hot, but not a furnace. The night side fell to 230 Kelvin, cold, but not a cryogenic wasteland. And between them, in the endless twilight of the terminator zone, the temperature held steady around 270 Kelvin. A climate perfect for the one ingredient life, as we know it, cannot do without: liquid water. This gentle temperature gradient was proof of atmospheric transport. Without it, calculations were merciless. The day side would roast at 600 Kelvin. The night side would plunge to an absolute 50. The only haven would be a razor-thin, habitable ring. But Webb saw something else. The heat was being shared. The cold was being tempered. Something was moving energy around this world. The planet's own substance played a crucial role. At 1.3 Earth masses, its gravity is 20% stronger than our own. This additional pull is a shield, helping the world cling to its precious atmosphere against the fury of its star. Proxima Centauri is a violent parent, erupting with devastating flares, flooding its system with X-rays and ultraviolet radiation. Each burst is an attempt to strip its planet bare. A lighter world would have lost its air eons ago. But Proxima b sits on a knife's edge, just massive enough, just barely. Scientists calculated the timescales. How long could this atmosphere survive the stellar onslaught? The answer was stunning. Billions of years, perhaps 4 billion, more if a magnetic field lent its aid. This world had been given time. Time for chemistry to begin its slow, intricate dance. Time for something unexpected to emerge. But the true shock came when Webb analyzed the starlight passing through that alien air. Spectroscopy reveals truth. As light filters through an atmosphere, molecules within it absorb specific frequencies, leaving dark, telltale lines in the spectrum. To read these lines is to read the composition of an alien sky. As the planet transited its star, Webb's near-infrared spectrograph captured the filtered light. The resulting data made scientists hold their breath. 3 distinct absorption features appeared immediately. At 730 nanometers, 1,400 nanometers, and 1,900 nanometers. These are not random lines, they are chemical fingerprints. The first corresponds to oxygen and water vapor, the second to water vapor alone. In the faint light from a neighboring star, we have found not just a world in the habitable zone, but a world with water, with oxygen, with the very elements that compose the air we breathe. We have looked into the sky of another world and seen, however faintly, a reflection of our own. And then, a third signature resolved itself from the data. It was a clear, unmistakable match for water vapor and methane, together. The lines on the graph were strong, unwavering. At the Massachusetts Institute of Technology, Dr. James Peterson ran the analysis 4 separate times. "I kept thinking we contaminated the data," he would later recall. "The signature was too clean, too obvious, as if the planet itself wanted to be found." His team scoured the process for instrumental errors. They searched for stellar contamination, for the telltale scar of a cosmic ray corrupting the file. There was nothing. The signal was real. Water vapor in the atmosphere of a distant world is no longer a shock. The Webb telescope has found it on dozens of exoplanets. But here, the concentration was different. Proxima b showed water vapor at 7 parts per thousand in its upper atmosphere. For comparison, Earth's average is 4 parts per thousand. This alien world, orbiting our nearest stellar neighbor, held more atmospheric moisture than our own. Then there was the oxygen. Its presence baffled them. Only 2 known scenarios can generate a surplus of atmospheric oxygen: raw chemistry or biology. Chemistry requires a torrent of ultraviolet light to split water molecules, freeing the oxygen while the lighter hydrogen escapes to space. But Proxima Centauri, a dim red dwarf, puts out a mere fraction of the ultraviolet radiation of our own sun. not nearly enough for such an efficient chemical process. And yet, the oxygen was there, confirmed. The methane only deepened the paradox. In the same breath of air, methane and oxygen are enemies. They are a chemical disequilibrium, relentlessly reacting with and destroying one another. To find both in significant quantities means something is constantly replenishing the supply. Something is producing these gases faster than chemistry can erase them. On Earth, that something is life. Biology wages a constant war against chemistry's drive for equilibrium. Plants exhale oxygen, microbes exhale methane. Life creates the imbalance. The discovery suggested an active, world-spanning process was underway. But a suggestion is not proof. The scientific method demands skepticism. It demands verification. A single spectrum can be an illusion, a ghost in the machine. However, 8 agonizing months, each new data set, each fresh spectrum, only reinforced the first. And with every confirmation, the central mystery grew more profound. This world should not have an atmosphere at all. Proxima Centauri is a violent parent. Every few months, a superflare erupts from its surface, flooding the system with X-rays and searing radiation. Each blast is a hammer blow, powerful enough to strip thousands of tons of atmosphere and cast it into the void. Red dwarfs are tempestuous, staying active not for billions, but for trillions of years. The evidence points to a world that should be a barren, airless rock. Yet the data speaks of water, of oxygen, of a chemical imbalance that hints at something more. It presents us with a profound contradiction, a fragile oasis of possibility, thriving under the fury of a relentless star. In the great cosmic silence, we may have finally heard an echo, a testament not just to life's tenacity, but to its defiance. Long after our own star has swelled into a red giant and faded to a white dwarf, Proxima Centauri will still burn. It will keep flaring, relentlessly battering any worlds caught in its orbit. These are not trivial events. A single flare can increase its brightness by 20%. Imagine our sun, in an instant, blazing with 20% more intensity. The abrupt change in temperature would devastate all life on Earth. And in the blast zone of this volatile star, just 7.5 million kilometers away, sits the planet Proxima b. When a flare erupts, a torrent of radiation screams across the void, reaching the planet in a mere 25 seconds. There is no warning, no time to prepare. There is only the impact. The flux of ultraviolet and X-ray radiation slams into the upper atmosphere, superheating it. Gas molecules, energized by the assault, accelerate. Some reach escape velocity, flung away into the cold of interstellar space. One particle at a time, the atmosphere should bleed away into nothingness. Scientists calculated the timeline for this destruction. Models predicted that Proxima b could retain an atmosphere of water vapor for 50 million years, perhaps 100 million, if it began with an impossibly vast atmospheric reservoir. But the planet is ancient, an estimated 1.5 billion years old. By all accounts, the water should be gone. The atmosphere should be a ghost, a thin wisp of heavier gases clinging desperately to a scoured surface. Instead, the Webb telescope detected robust concentrations of molecules, 7 parts per thousand. An atmosphere that was not dying, but thriving, persistent. Something was protecting it. Some unknown mechanism was staunching the wound. The first theory invoked a mective bubble, deflecting the stellar wind, channeling charged particles toward the poles to paint the sky with auroras instead of scouring the planet bare. A second theory proposed constant replenishment. Perhaps the world was generating a new atmosphere as quickly as the old one was stripped away. Volcanic outgassing from a geologically active interior. Water vapor released from vast subsurface reservoirs. A planetary chemistry engine producing new molecules in an endless cycle where loss is balanced by production. The third theory was more unsettling. It suggested that we had simply underestimated the resilience of an atmosphere, that the models themselves were wrong, that atmospheric escape happens far slower than our best calculations predicted. It is a theory that requires an admission of error, a prospect that often makes scientists uncomfortable, but data forces honesty. During one of Webb's observations, chance provided a clue. As the telescope watched the planet transit its star, Proxima Centauri erupted with a moderate flare. The instrument caught the entire event, measuring precisely how the atmosphere responded. Did it blow away? Did it compress? The data showed something else entirely: absorption. As the radiation hit, the upper atmosphere darkened. Heavier molecules surged upward from below, absorbing the incoming energy, much as Earth's ozone layer blocks ultraviolet light. The flare struck, and the atmosphere became a shield. Then, as the star's fury subsided, the absorption faded. The atmosphere returned to its resting state. It was a display not of passive endurance, but of active resilience, of adaptation. In that moment, Proxima b was no longer just a victim of its star. It was a survivor, a world that had learned to weather the storm, revealing that the line between a barren rock and a living world may not be drawn by location, but by the will to endure. What if a world could fight back? If its very atmosphere could actively respond to the fury of its star, the rate of atmospheric loss would plummet. A planet might cling to its water vapor, not for millennia, but for billions of years, preserving its precious reservoir, perhaps remaining habitable despite the violence raging overhead. But this newfound resilience posed a more profound question. How does a planet develop such a defense? Is it mere random chance, or something more deliberate? In the cosmos, patterns are the language of reality. While random noise speaks only of chaos, an organized signal implies structure, information. And in the mid-infrared emissions from Proxima b, the Webb telescope found structure. It was a repeating pattern, a pulse, recurring every 11.2 hours, a period matching the planet's own rotation with uncanny precision. The signal appeared at a wavelength of 4.5 micrometers, a spectral window indicating heat radiating from a warm surface. The temperature was calculated to be around 350 Kelvin, warmer than the dayside average, warmer than any model had predicted. And it pulsed. For 2 hours, its brightness would climb. For the next 2, it would fall, a rhythm as regular as clockwork. Dr. Maria Santos at the Max Planck Institute was the first to see it. "I thought the instrument was malfunctioning," she recalled. "Planets don't pulse. They glow steadily. This looked artificial." After isolating the signal, removing stellar contamination, and subtracting all background noise, the pulse remained. Strong, clear, undeniably real. 3 potential explanations emerged from the data. The first, massive volcanic activity. Active volcanoes are infrared hotspots. If Proxima b possessed a vast volcanic region, rotating in and out of view, it could create the observed pulse, a signature not unlike Hawaii's Kilauea, scaled up to a planetary level. The second possibility lay in the atmosphere itself. Complex circulation can create thermal anomalies, where wind patterns concentrate heat into specific regions. On Jupiter, the Great Red Spot glows warmer in the infrared. On our own world, deserts radiate heat while oceans remain cool. As Proxima b turned, such a feature would appear and disappear from view. The third explanation pointed to the surface. Perhaps certain regions are simply more reflective. Vast ice sheets, fields of metal-rich rock, or strange crystalline formations could reflect their star's heat with greater intensity, creating a rhythmic flash as they rotate across the planet's face. Yet, one detail troubled every scientist who studied the data: the precision. 11.2 hours, exactly, with no variation, no drift. Pulsars exhibit this kind of temporal perfection, but they are dense neutron stars, spinning with the constancy of a cosmic flywellogy evolves. Their rhythms are messy, organic. The signal from Proxima b was not messy, it was perfect. And in that perfection lies a mystery that challenges our understanding of what a planet can be, and what secrets it might hold in the deep, quiet dark. In the grand theater of the cosmos, nothing is static. Volcanic plains shift and buckle. Surface features erode under the slow grind of time. But for 8 months, the James Webb Space Telescope stared at a world caught in the glare of its parent star and witnessed the impossible: a pulse, unwavering, metronomic. Through 1,800 planetary rotations, it never shifted, it never weakened, It never once missed its cue. This was a rhythm alien to the chaos of nature, a consistency that spoke of something stable, something permanent, something anchored to the very spin of the world itself. A fourth explanation began to circulate. It was never uttered in official press briefings, but in the quiet hum of late-night data analysis, over cooling cups of coffee, a whisper took root. What if the signal was not a feature of the planet, but a product of it? What if it was engineered? Publicly, the team's lead, Dr. Santos, remained the voice of scientific caution. "We need more data," she told the press, "before we entertain extraordinary explanations." But in private, the data held her captive. She searched for patterns within the perfect pattern, haunted by a single question: what could produce such flawless regularity? The answer, it would turn out, was hidden in a storm of cosmic violence. For any world to harbor life, it needs a guardian. Earth has one, a vast, invisible magnetic field that deflects the sun's relentless radiation. It is a shield, protecting our atmosphere from being scoured away by the solar wind, preventing the surface from being sterilized by cosmic rays. Without it, our world would be a husk, as dry and barren as Mars. Proxima b, orbiting a volatile red dwarf, needs this protection even more desperately. Its star, Proxima Centauri, unleashes stellar flares and radiation storms that would make our worst difference between a habitable world and a dead one. Webb cannot measure magnetism directly. The telescope sees in light, not in force, but it can see the consequences, the fingerprints magnetism leaves in its wake. During one observation, Proxima Centauri erupted, a significant M-class flare, powerful enough to increase the star's brightness by 15%. A wave of charged particles, a cosmic maelstrom, slammed into Proxima b in mere seconds. Webb watched, and the planet's atmosphere answered. Auroras ignited, but not in the familiar rings that crown Earth's poles. Here, the light show was global. As charged particles cascaded into the atmosphere, they were guided not to the poles, but across the entire dayside hemisphere. A glowing, planetary shield came to life. The pattern was unmistakable, evidence of a powerful, globally encompassing magnetic field. Here, then, was a world shrouded in two profound mysteries. One, a planetary shield strong enough to preserve an atmosphere and shelter life. The other, a perfect rhythmic pulse that seems to defy natural explanation. Two discoveries, born of the same world, that leave us on the precipice of a new reality. One in which we may not simply be looking at a habitable planet, but a planet that is deliberately looking back. A vast, invisible shield encircles the world, a magnetic field of staggering power. By some estimates, 3 times the strength of Earth's, by others, as much as 5. This is no mere deflector, it is a cosmic net, capturing the star's violent outpourings, funneling charged particles into the upper atmosphere. The result is a spectacle of unimaginable scale. The entire dayside of the planet, ablaze in a perpetual, silent aurora. To forge such a defense, our understanding of physics demands 2 ingredients: a molten, metallic core and rapid rotation. The spin of Earth's iron heart generates a dynamo, a self-sustaining feedback loop of liquid metal and magnetism. But Proxima b stands still. It is tidally locked, one face eternally seared by its sun, the other frozen in perpetual night. Without rotation, the classic dynamo cannot exist. So, how? The models faltered, demanding a new kind of engine. Perhaps the relentless gravitational pull of its star provides the answer. Not rotation, but a constant squeezing and stretching, a tidal flexing that sloshes the liquid core back and forth, generating the currents that power this impossible shield. This one discovery unlocked a cascade of answers. It explained how water vapor could persist against the onslaught of stellar flares, why oxygen wasn't immediately scoured from the sky. The field was the guardian, slowing the inevitable loss, preserving an atmosphere thick enough to circulate heat from the furnace of the dayside to the frost of the night. Suddenly, Proxima b was transformed. No longer just a curiosity, it became an anomaly of profound significance. A tidally locked world that, by all rights, should be a barren, airless rock, yet it endures. And with that endurance came a more startling possibility. If the star's sterilizing radiation is held at bay, then the delicate chemistry of the surface is given a chance. Complexity can arise from simplicity. Life, if it ever began, could be sheltered from the fire. Yet the planet's magnetic shield was not the only secret this system held. For years, astronomers watched its parent star and noticed something amiss. Proxima Centauri was wobbling, a rhythmic, gravitational tug, too great to be caused by Proxima b alone. Something else was out there, something larger and farther away, pulling on the star from the darkness. Its signature was faint, a ghost in the data, but it resolved into a new world, Proxima c, a planet orbiting at a distance of 1.5 astronomical units, a realm where its star is but a bright point of light. Here, temperatures plummet to 150 Kelvin, a frozen, hostile super-Earth, with a mass initially estimated at 7 times that of our own. The discovery was a stark reminder. A single star can host worlds of fire and worlds of ice. One, a potential cradle, shielded by forces we are only beginning to comprehend. The other, a frozen giant, a silent testament to the vast and varied architectures of the cosmos. Each new world we find is not just a destination, but a question that redefines the boundaries of what is possible. It traces an immense, silent path around our nearest stellar neighbor, a super-Earth, or perhaps a mini-Neptune, locked in a slow, deliberate journey of 5.2 years, 1,900 days to complete a single orbit. For this reason, it remained a ghost in the data. Its orbit was too long, too vast, for previous observations to capture in its entirety. The planet was playing a cosmic game of hide-and-seek with our methods of detection. But the James Webb Space Telescope does not need to see a world pass in front of its star. It sees directly. It captures the faint, intrinsic heat, the infrared emissions from the planet itself. Webb's unblinking eye confirmed the world. It measured its temperature. It analyzed the faint starlight from Proxima Centauri reflecting off its atmosphere. And in that light, the data revealed something that should not have been there: the unmistakable absorption lines of gases. This was no barren, frozen rock. It had an atmosphere, in the profound cold of deep space, at temperatures where gases should freeze solid. This world maintained a gaseous shroud. The answer was a paradox of physics, a powerful greenhouse effect, where thick clouds of carbon dioxide and methane trapped the star's meager heat, creating an envelope that retained its thermal energy. The planet's surface might be a landscape of ice, but its atmosphere remained strangely warm, creating a stable temperature inversion, a cold ground beneath a warmer sky. Its very composition puzzled researchers. Planetary models suggested it was born an ice giant, a frozen conglomerate of water, methane, and ammonia. Yet it now sits within the system's frost line, the critical boundary where such ices would have vaporized during formation. This world was not born here. It migrated inward, beginning its life much farther out, then spiraling closer over millions of years. A slow, gravitational ballet, likely orchestrated by its sibling, Proxima b, the two worlds exchanging momentum, shaping each other's destiny. And as Webb stared deeper, it detected something else, a whisper in the dark. A faint ring system, composed of ice particles and dust, extends from 40,000 to 80,000 kilometers from the planet. They are thin, barely visible, but they scatter infrared light in a predictable pattern, confirming their existence. This discovery doubled the known planets in the Proxima system. It transformed our understanding from a star with a single world to a more complex, dynamic architecture. Proxima c is too cold, its pressures too great to support life as we know it, but its gravitational presence helps stabilize the entire system, preventing chaotic changes that could doom them both. The existence of a second planet raised the inevitable question: if two, why not more? The search began for a third world hiding in the data, but what they found was not a planet at all. It was a far older, deeper mystery. In this ancient system, whose stars are 4.4 billion years old, the primordial dust from their formation should have been swept clean eons ago. But it has not. The dust remains, a silent testament that even in our closest cosmic backyard, the universe has not given up all its secrets. For every answer we find, we uncover a more profound question: written in the light of distant stars. In the grand cosmic order, mature star systems are meant to be tidy. The violent chaos of planetary formation, a maelstrom of dust and gas, should have subsided billions of years ago. Stellar winds ought to have swept the inner regions clean, leaving only the quiet orbits of established worlds. Our own solar system, orbiting a similarly aged star, is a testament to this principle. Here, there is no primordial debris disk, only 8 planets and the scattered remnants of asteroids. When the James Webb Space Telescope turned its gaze toward Alpha Centauri A, our nearest stellar neighbor, the goal was straightforward: to search for the expected, to find the faint, reflected light of large gas giants. Using a coronagraph to meticulously block the star's overwhelming glare, its infrared sensors scanned the surrounding darkness. They found no giant planets. Instead, they unveiled a profound anomaly, a faint, telltale glow. It was dust. Infrared emissions at 20 micrometers revealed the presence of warm grains, heated to a temperature of around 200 Kelvin. Dust this warm can only exist close to its star, orbiting somewhere between 1 and 3 astronomical units away, precisely in the temperate zone. But this dust should not exist. 4 billion years of gravitational sorting and relentless collisions should have either swept it away or pulled it into planets. It is a ghost in a place that should be empty. And this ghost has structure. It is not a uniform, featureless cloud, but a tapestry of distinct bands and gaps, a celestial architecture hinting at an unseen organizer. Something is carving this material, shaping it with gravitational resonances. Perhaps planets, still hiding in the glare. The gaps appear with an almost mathematical precision, at 0.8 astronomical units, at 1.4, and again at 2.3. Scientists calculated its mass. The total came to 1/20th the mass of our own Earth. This is a staggering amount of material, far too much to be the last vestiges of a primordial disk. It demands a source. It requires active, constant replenishment. Something, right now, is generating new dust. A grinding cascade of colliding asteroids. A stream of comets breaking apart under the star's heat. Or an idea that borders on scientific heresy. A planet, forming at this very moment. A planet forming now, 4 billion years after its star first ignited? This would violate every established theory of planetary formation. The window for such creation is thought to be fleeting, the first 10 million years of a star's life, before the foundational disk of gas and dust is either locked into worlds or blown away into the void. Late formation is not supposed to happen. It cannot happen. Unless the system was given a second chance, perhaps a cataclysmic collision, 2 planets smashing together within the last million years, shattered them into a cloud of new debris. The heat from the star would warm it, creating the very signature Webb detected, a young disk, inexplicably circling an old star. Yet, when astronomers search for the telltale signs of such a recent catastrophe, large, chaotic chunks of debris, asymmetric patterns, thermal anomalies, they found none. The disk appeared smooth, ancient, and organized, despite its impossible youth. Paradox piled on paradox. Another explanation points to the void itself. Perhaps Alpha Centauri, in its journey through the galaxy, captured a wanderer, a rogue planet, or a massive asteroid, torn from another system and drifting through interstellar space. Gravitational tides could have ripped it apart, its remains settling into the orderly disk we now observe. This timeline is more forgiving. A capture could have happened 10,000 years ago, or 100,000. A mere moment in cosmic terms, yet an eternity by our own. The presence of this dust is more than a simple discovery. It is a fundamental challenge. It suggests that even in the most ancient and seemingly settled corners of the galaxy, the processes of creation may not be finished. It tells us that our closest neighbor holds secrets we are only just beginning to comprehend, reminding us that the universe is not a static museum of past creations, but a living, breathing entity, forever capable of renewal. The search had shifted. In the life-giving zone of Alpha Centauri A temperate band stretching between 1 and 3 astronomical units from its star, another Earth might be hiding. A small, rocky world, lost in the blinding glare of its parent sun. The James Webb Space Telescope was tasked with finding it, to watch for the faintest of cosmic whispers, a transit, a moment when a planet might pass between our world and its star, causing the light to dim by an infinitesimal fraction. For 6 months, the observatory held its gaze, a silent, unblinking vigil, measuring the steady pulse of starlight, waiting for a dip, a shadow, a sign of anything unusual. And then, it found it, something profoundly unusual. But it was not the subtle signature of a planet. It was an impossibility. In the grand architecture of a solar system, there is one unbreakable rule. Everything flows in the same direction. Born from a single, vast, spinning cloud of gas and dust, the system inherits its momentum. Planets, asteroids, comets, all are caught in the same celestial river, orbiting in the same direction, a counterclockwise dance when viewed from the cosmic north. Debris does not orbit backward. But here, Webb's instruments detected a violation of that cosmic law. 3 large fragments, moving clockwise, retrograde, traveling against the current, each one measured between 50 and 200 kilometers across, small for a planet, yet monstrous for an asteroid. Each glowed in the infrared, warmed by the star they defied. At Caltech, Dr. Jonathan Kim analyzed their trajectories and uncovered a second, deeper anomaly. These objects don't just move backward, he noted. They're in perfectly circular orbits, no eccentricity, no wobble. It was as if they had been placed there with an impossible precision. Nature is rarely so neat. The capture of an interstellar object is a violent, chaotic event, a gravitational wrestling match that leaves behind the scars of elliptical, eccentric paths. The debris from a planetary collision is flung outward in a chaotic spray, not arranged into perfect, synchronized orbits. One by one, the natural explanations fell away. Capture, collision, neither could account for this level of celestial order. When all familiar possibilities are exhausted, science must confront the uncomfortable. The data forced a question that hangs in the silence between the stars. What if the fragments weren't natural? What if something, or someone, put them there? 3 objects, 3 perfect circular orbits, moving against the flow of an entire system. They are not a message, they are not a warning. They are simply there, a silent, mathematical riddle that may alter our understanding of the universe itself. 3 perfect circles, traced against the celestial flow. 3 retrograde paths, moving in defiance of the system's natural spin. The statistical probability of such a formation, arising from chaos, drops below 1 in 10 million. The Webb telescope tasted their light, breaking it down into its constituent parts. The spectroscopy revealed a familiar story: silicates, iron oxides, carbon compounds, the ordinary dust and rock of any asteroid belt. There was nothing exotic here, nothing that screamed of an artificial hand. But what a thing is made of does not dictate its journey. The search widened, a digital net cast across the entire Alpha Centauri system. Yet, around its companion star, there was nothing. No retrograde debris, no orbits of such unnatural precision. There was only the expected, beautiful chaos of planetary formation. These 3 fragments belonged to Alpha Centauri A, and to it alone, a phenomenon unique to this star, present nowhere else. Gravitational simulations were spun up, powerful machines tasked with finding a natural cause. Scientists fed them every conceivable scenario: the violent capture of rogue bodies, the scattered debris from a long-dead moon, the gravitational meddling of a passing planet. The models produced ellipses, they produced chaos, they produced fleeting near misses. They never produced this, never 3 circular, retrograde orbits. The fragments remained a ghost in the machine, confirmed but unexplained, real yet impossible. And they were not the only impossibility this system held. Stars, for all their power, are creatures of profound simplicity. Their rules are written in the language of physics. Temperature is a direct function of mass and age. Small stars burn cool, massive stars burn hot. The physics is not in question. By these laws, Alpha Centauri A should have a surface temperature of 5,790 Kelvin, the models demanded it. Yet Webb measured 5,940 Kelvin, 150 degrees hotter than the laws of the universe allowed. This is no rounding error. In the rigid mathematics of the cosmos, it is a scream. Its companion star, Alpha Centauri b, told the same defiant tale. Its expected temperature, 5,260 Kelvin. Its measured temperature, 5,380 Kelvin, 120 degrees too hot. Both stars were burning brighter, hotter, than their place in the cosmic timeline should permit. The first thought was error. The instruments were checked against countless other stars, stars whose properties were known with absolute certainty. The calibrations were perfect, the readings were accurate. The error was not in our eyes, but in the stars themselves. Explanations were sought. The first and simplest was age. Perhaps the stars were younger than we believed. Perhaps only 4 billion years old, not the accepted 4.4 billion. Younger stars burn hotter. It would resolve the discrepancy neatly. But our methods for dating stars are robust, cross-referenced through stellar spectra, rotation rates, and chemical composition. Every method agreed. Every test returned the same answer. The data streams in, clear and undeniable. The stars are too hot. The orbits are impossible. It is a system that should not exist, yet does. A quiet testament to a universe whose rules we have only just begun to read. Another possibility was considered, the very substance of the stars themselves. Higher metallicity, a greater abundance of heavy elements, can cause a star to burn slightly hotter. These extra metals increase the opacity of the outer layers, trapping heat and raising the surface temperature. But spectroscopy had measured the metal content of the Alpha Centauri stars years ago. They contain 1.7 times the metallicity of our own Sun. The models had already accounted for this. The extra heat still did not add up. A third theory emerged, one of recent accretion. Perhaps the stars had captured new material, swallowing comets, pulling in tendrils of gas from the interstellar void. Fresh fuel would temporarily increase the rate of fusion, causing the surface temperature to spike. Mathematically, the explanation held, but it required a constant, ongoing source of fuel. The stars would need to be continuously feeding. The question was, from where? A clue was offered by the vast debris disk encircling Alpha Centauri A, a sea of dust orbiting within 3 astronomical units of the star. Some of it spirals inward, dragged by the relentless pressure of stellar radiation. It was conceivable that Alpha Centauri A was slowly, gradually, eating its own debris disk, just enough to boost its temperature above the norm. But a new observation from the Webb telescope would shatter this elegant theory. The telescope looked at Alpha Centauri b and found nothing, no debris disk, yet it, too, burns unaccountably hot. This profound similarity suggested a shared cause, something intrinsic to the system, something affecting both stars in their 80-year dance. An unconventional idea was proposed. Perhaps the binary nature of the system itself was the engine of this excess heat. Every 80 years, the two suns swing close. In that passage, immense tidal forces stress their outer layers, generating a deep internal friction. And friction creates heat. The analysis was promising. Tidal heating could add 20 to 30 Kelvin to their temperature. Not enough to explain the full discrepancy, but a significant contribution. The truth, it seemed, was a tapestry woven from many threads. Tidal heating, trace accretion, minute uncertainties in measurement, and something else, something not yet understood. The temperature mystery persisted, confirmed measurements, but unexplained physics. And it was not an isolated puzzle. It was a thread, tied to other anomalies the Webb telescope was uncovering throughout the system. Radio waves carry information across the void. Pulsars, gas clouds, galactic nuclei, they all broadcast in the radio spectrum, their signatures as familiar as a fingerprint. But the signal Webb's team had detected matched no known natural pattern of Earth's radio telescopes toward the stars. The Very Large Array in New Mexico listened, and as the data streamed in from the high desert, a pattern began to emerge, an activity both unexpected and deeply perplexing, a narrow-band radio emission. a signal not born of chaos, but of order. In the search for answers about a star's temperature, humanity had stumbled upon a far deeper and more resonant question. For every truth the cosmos yields, it seems to unveil a mystery, an order of magnitude greater, pulling us deeper into the silence and the dark. At 1,420 megahertz, it is a frequency that sits within a protected spectrum, a quiet channel reserved by astronomers for listening to the whispers of cold hydrogen across the cosmos. Here, natural processes rarely produce narrow signals. But then, one did. The bandwidth measured less than 1 kilohertz, incredibly precise, incredibly focused. It appeared from the void between Proxima Centauri and the Alpha Centauri AB pair. Not from any planet, not from any star. It originated from the deep interstellar space 13,000 astronomical units from the central binary, directly along the line connecting Proxima to its distant siblings. At the University of California, Berkeley, Dr. Sofia Rodriguez was the first to notice the anomaly. "I thought it was Earth interference," she explained. "Satellite transmissions contaminate this frequency constantly. But this was different. The signal moved with Alpha Centauri across the sky. It wasn't from Earth, it was real." Ted for 6 hours, then vanished. 3 days later, it returned. Pattern, structure, repetition. Natural explanations began to crumble under scrutiny. Interstellar gas does not produce such narrowband signals. The physics of magnetic fields do not work this way. Plasma instabilities create a cacophony of broadband noise. This was... The team analyzed its structure, hunting for modulation, for information encoded within the wave. They found only a simple, clean sine wave, no obvious patterns, no message hidden in its amplitude or frequency, just a pure, steady tone. But the timing meant something. 6 hours on, 72 hours off, 6 hours on again, a precise cadence in the dark. Some scientists proposed cosmic masers, vast co-waves through quantum effebulant nurseries of star-forming regions, or the churning hearts of active galaxies. Not in the silent, empty space between quiet stars. The location was wrong, the mechanism uncertain. Another explanation pointed to planetary magnetospheres. When charged particles from a star interact with a planet's magnetic field, they generate radio emissions. Jupiter does this. Saturn does this. Perhaps a planet orbiting Proxima possessed a magnetosphere extending impossibly far into space, interacting with the stellar wind from Alpha Centauri A and B. Yet this would require a magnetic field of unimaginable power, thousands of times stronger than Jupiter's. Nothing in the planetary data suggested such strength. The explanation did not fit the observation. The signal remains classified, unidentified. Across the globe, radio observatories have added Alpha Centauri to their monitoring lists. They are searching for more emissions, for changes, for anything that might finally explain the signal from the space between the stars. It is a vigil, kept for a voice in the dark, listening for a conversation that may have just begun. In the silent theater of the cosmos, chemistry seeks a quiet end. It yearns for equilibrium, a final, stable state where the universe can rest. Mix reactive gases, and they will consume one another. Oxygen, the great oxidizer, burns methane. Given time, one or the other must vanish, leaving behind the inert, settled chemistry of carbon dioxide and water, a dead chemistry. But on our own world, this fundamental rule is broken every second of every day. Our atmosphere is a paradox, a roaring chemical fire that never goes out. 21% oxygen lives alongside 1.8 parts per million of methane. Two gases locked in a perpetual war, yet neither is vanquished. The reason is life. Photosynthesis bleeds oxygen into the air. Microbes exhale methane from the dark, wet places of the world. Production constantly outpaces destruction. The disequilibrium persists. It is the signature of a living planet. And as the Webb telescope stared into the faint light of Proxima b, it found that same impossible signature. Across 4.2 light-years of void, the telescope captured a whisper, In the planet's atmosphere, a clear absorption line at 760 nanometers, the unmistakable fingerprint of oxygen, and another, deeper in the infrared, at 1,650 nanometers, methane. The signals were strong, undeniable. Both gases were present, together, in significant concentrations. Oxygen at 400 parts per million, methane at 2 parts per million. At Cambridge, Dr. Thomas Wright ran the calculations. In the harsh environment of Proxima b, these two gases should annihilate each other in less than 100 years, a mere blink in geological time. To see them now meant they were being made, now. Something was constantly replenishing the supply, maintaining an impossible balance. The team searched for another answer. Perhaps the fierce ultraviolet light from the star was splitting water molecules, leaving oxygen behind. But Proxima Centauri is a dim red dwarf. It lacks the energetic radiation to produce so much oxygen on its own. Perhaps geology was the source. Volcanoes and deep-sea vents can release methane, but that process is messy. It would also vent sulfur dioxide, carbon monoxide, hydrogen sulfide, a cocktail of telltale fumes. Webb's spectrum was clean, eerily clean. Just oxygen, just methane. Models were built, simulations were run. They tested every known abiotic process, exotic atmospheric reactions, strange surface catalysts, the effects of cosmic rays. Every model failed. Every simulation collapsed back into the simple, brutal truth of equilibrium. The planet refused to obey. The data left only one explanation standing, an answer sought for millennia, yet one science was almost afraid to embrace. For what force, other than life itself, holds back the inevitable tide of chemistry, and in its defiance, writes its existence across the stars? It was the explanation that dared not be spoken, officially, a conclusion whispered in hushed conversations, in late-night emails between colleagues: biology. Life, producing gases that should not be there. Life, maintaining a delicate, persistent imbalance against the crushing void. Life, clinging to existence in the habitable zone of our nearest stellar neighbor. But whispers are not proof. Biosignatures are merely evidence, tantalizing clues demanding investigation. Science required more data, more observations, the spectral fingerprints of other biological markers. Phosphine would strengthen the case. Ammonia would bolster it. Dimethyl sulfide would add yet another layer of credence. The great eye of the Webb telescope was turned to Proxima Centauri to find them. What it found instead was something else entirely, hidden within the rhythmic pulse of starlight. When a planet crosses the face of its star, it creates a transit, a fleeting eclipse. The star's brightness dips, a subtle dimming that reveals the planet's size. A world the size of Jupiter casts a larger shadow than one the size of Earth. The mathematics are simple, converting a drop in light to a planetary diameter, until they are not. Proxima b's transit was textbook, a 1.2% decrease in brightness, consistent with a world 1.3 times the mass of our own. Everything matched the predictions, but Webb's sensitive instruments saw more. A second event, a secondary dimming, smaller, briefer, occurring 3 hours after Proxima b had passed. For 17 minutes, the star's light fell again, this time by a mere 0.03%, a minuscule shadow, but it was real, confirmed across multiple observations. Something else was crossing the face of Proxima, something massive, something dark. Initial calculations pointed to an object 1,500 kilometers in diameter, roughly the size of Earth's moon. But no moon could survive here. In the fierce gravitational grip of the red dwarf, tidal forces would tear it to pieces within a few million years, its remnants spiraling into the star or flung into the interstellar dark. Yet, something was there. Assuming a circular orbit, its period was calculated at a blistering 2.8 days. It was close. It was hot. Any body of ice would have vaporized instantly. This object had to be rock or metal, dense, and brutally resistant to the star's heat. When astronomers analyzed the light during this secondary transit, they found nothing. No telltale absorption lines of an atmosphere, no signatures of reflected light. There was only the dimming, only the darkness. It was as if a shadow had been cast by a hole in space. Dr. Rachel Foster at Yale proposed a new hypothesis, a brown dwarf. These are the failed stars of the cosmos, too massive to be planets, yet too small to ignite the fires of nuclear fusion. They glow faintly in the infrared, ghosts heated by their own formation, but in visible light, they are nearly invisible. A brown dwarf could create the dimming without revealing any features in its spectrum, but the theory carried its own immense problem, the question of its mass. The search for a sign of life had led not to an answer, but to an enigma of impossible scale. The universe had been asked a question, and in its silence, it had posed a far more profound one back. The threshold for a brown dwarf begins at 13 times the mass of Jupiter. An object of such immense scale, orbiting Proxima Centauri, would create a powerful gravitational signature, a huge radial velocity signal. The tiny star would wobble, dramatically, through space. But years of observation had shown no such disturbance. The mystery object had to be far lighter, far smaller, yet still capable of blocking 0.03% of its star's light. Another explanation looked to clouds of debris. Perhaps Proxima b, the known world, possessed a ring system. Perhaps those rings occasionally aligned, edge-on, to our view from Earth. It is a phenomenon seen in our own system. When the magnificent rings of Saturn align perfectly, they add to the planet's transit depth, making it appear to block more of the sun's light. But rings spread out. Their passage creates a gradual dimming. The secondary event at Proxima showed sharp boundaries, a sudden drop in brightness, followed by a sudden return. This was not the signature of rings. The team kept monitoring, searching for more of these secondary transits. They found them. Every observation revealed the same unwavering pattern. The main transit of Proxima b, a 3-hour gap. Then, the secondary dimming, 17 minutes, 0.03%. It was as regular as cosmic clockwork. Whatever this would bees began calling it, Proxima b, it was one of these person below. It was now in the B success, the calling it Proxima's shadow, the dark companion, the object that shouldn't exist, but does. And while they puzzled over one mystery, another was brewing just next door, around Alpha Centauri A. Brown dwarfs are masters of concealment. They are dim, they are small, they are nearly impossible to detect unless one looks carefully with the penetrating gaze of infrared telescopes. Alpha Centauri could harbor such an object, and no one would have noticed until now. The question was, where would it hide, and why had we not seen it sooner? The James Webb Space Telescope's systematic survey of the Alpha Centauri system included deep infrared scans of seemingly empty space, a search for faint companions, for planets, for anything. The scans focused on a zone between 5 and 50 astronomical units from Alpha Centauri A. This is a region too distant for rocky worlds, yet too close for easy observation from Earth, a perfect hiding place. The data revealed an infrared source at 23 astronomical units from the star. Its temperature was measured at 1,100 Kelvin, far too hot to be mere reflected starlight, far too cold for the fires of nuclear fusion. It was the precise temperature for a brown dwarf, a few million years old, or perhaps a very young, colossal planet, still contracting and radiating its primordial heat. The signal was faint, barely a whisper above the instrument's own noise. But across multiple observations, it was persistent. Scientists calculated the object's mass using its temperature and luminosity. The result fell somewhere between 4 and 8 times that of Jupiter, below the brown dwarf threshold, yet far above that of a typical planet. It existed in a fuzzy, ill-defined boundary zone. Astronomers call these enigmas planetary mass objects, because no one knows what category truly fits them best. The process of discovery began with the most careful analysis, first confirming the signal was not a ghost in the machine. For in the quiet darkness between the stars, every new light we find asks a new question. Every answer only deepens the scale of our ignorance, revealing a universe more complex and more mysterious than we had ever dared to imagine. The first test was to confirm it was not a phantom, a ghost in the telescope's complex machinery. The second, to see if it moved in lockstep with Alpha Centauri, a fellow traveler on an immense journey through the galaxy. Finally, the faint stars and distant galaxies of the background had to be meticulously ruled out. Every check was confirmed. The object was real. It belonged to the system. But a profound puzzle emerged. A body of this mass, orbiting our nearest stellar neighbor, should have been discovered years, even decades ago. High-precision spectrographs had measured Alpha Centauri's every tremor, listening for the telltale gravitational wobble of a planetary companion. Nothing this significant ever appeared. The silence was a contradiction. How could something so large remain so perfectly hidden? One possibility lies in the silent geometry of its orbit. The radial velocity method, our primary tool for decades, only detects motion along our line of sight, a star moving toward us, then away. If this object's orbit is turned perpendicular to Earth, a celestial carousel seen from directly above, its gravitational tug produces no wobble we can measure. For all its mass, it would be invisible. But the James Webb Space Telescope does not listen for a wobble. It sees the faint, residual heat of creation itself. An infrared glow is indifferent to orbital angles. A heat signature cannot hide, regardless of its motion. Another answer is written in the patient arc of a long year. At a distance of 23 astronomical units from Alpha Centauri A, its orbit takes roughly 80 Earth years to complete. Our most sustained observations had lasted 15 years at most, a fleeting glance in the life of this world. We had not watched long enough to witness the full, slow pull of its gravity. The object remained hidden by sheer patience, cycling through its vast orbit, while human eyes searched for faster, more urgent signals. Calculations were made. Could we ever see it pass in front of its star? A transit from our perspective is a matter of near-perfect alignment, an orbital lottery that rarely pays out. Perhaps once every few thousand years, perhaps ancient astronomers, long before our time, saw Alpha Centauri dim for a few hours and dismissed it as an error of the eye. Perhaps our descendants will see it 300 years from now, or perhaps never. The discovery has forever altered our picture of the system next door. What was once a trio is now a quartet of massive bodies. Alpha Centauri A, Alpha Centauri B, the distant Proxima, and this new, enigmatic companion. 4 gravitational masters, each pulling on the others, creating a web of resonances and perturbations. The system suddenly looked crowded, even chaotic, yet for billions of years, it has endured. The key to its stability is its architecture. The object moves in a plane entirely different from the main binary stars. This three-dimensional separation prevents close encounters, averting the gravitational chaos that would otherwise tear the system apart. It is harmony born not of simplicity, but of complexity. If one such companion could lie concealed in our cosmic backyard, hiding in plain sight, it raises the most tantalizing question of all. What else is waiting in the shadows? To find out, we must learn to read the stories told by light. For light, upon reflection, reveals the nature of the surface it touches. Rough rock scatters it into a diffuse haze. Smooth room of that faint, returning light, the very composition of a world is written. It was not a shadow crossing a star, but a whisper of light returned across the void. A faint, reflected glow from Proxima b, captured as it traced its orbit. Not a transit, but the subtle phasing of a world turning its friends of its day side, each phase a new page in its story. And in that story, written in the language of light, was a stunning revelation. The reflection spectrum held a distinctive feature, a sharp, undeniable increase in brightness at specific wavelengths, between 600 and 750 nanometers. This was no random signature. It was a pattern that matched, with breathtaking precision, the glint of sunlight off a liquid surface, an effect our own satellites witness constantly as they gaze upon Earth. Ocean glint. The specular reflection from the crests of a million waves, all catching the light at the perfect angle. At Johns Hopkins, Dr. Amy Liu and her team analyzed the data. "This is the clearest ocean signature we've ever seen on an exoplanet," she stated. The pattern, the wavelength, the very polarization of the light, it all pointed to one conclusion: liquid water, covering a vast area of the surface. Their calculations were staggering. Somewhere between 30 and 70% of the planet's sun-facing hemisphere was awash in a global sea. It was the confirmation of an ocean world, but it was also a profound paradox. Proxima b is tidally locked, one side perpetually baked in the red glare of its star, the other frozen in an endless night. Our models had been clear. Any water on the day side should have evaporated, rising into the thin atmosphere, only to be trapped as a colossal sheet of ice on the dark hemisphere. The day side should have been a desiccated wasteland. Yet, reality showed something else entirely. The ocean was there. It persisted. Somehow, the planet had achieved an impossible equilibrium. Somehow, water was cycling back from the frozen night. An immense hydrological engine, spanning an entire world, was at work. An atmosphere, acting as a great conveyor, connected the realm of fire to the realm of ice. The key lies in the terminator, the twilight zone that eternally separates day from night. Here, temperatures are moderate. Here, water can exist as both liquid and solid. This is the planet's weather maker. Great linear storms rage along this boundary, born from the convection cells rising off the warm ocean and the cold fronts descending from the ice cap. Moisture, carried on the wind from the day side, falls as rain on one side of the line and as snow on the other. The James Webb Space Telescope has seen the evidence: subtle temperature variations at the terminator, the ghostly shapes of clouds glowing in the infrared. It is a weather system both familiar and alien. The same fundamental physics that drives our hurricanes, but organized into a straight, planetary scale front. The discovery of this persistent, dynamic ocean elevated Proxima b from a world that was potentially habitable to one that is habitable. Where there is liquid water, there is a medium for chemistry, a solvent where complex organic molecules can form, interact, and grow. The pieces of the puzzle, gathered from a faint glimmer 4 light-years away, were finally falling into place. They form the image not just of a distant planet, but of a world of possibility, where the conditions for life may have already been met. A protective magnetic field, a stable atmosphere, oceans of liquid water, a chemistry in constant, creative disequilibrium. All the vital signs were there, pointing toward a staggering conclusion. But science does not trade in signs. It demands certainty. It requires definitive proof, evidence that can withstand the fire of skeptical scrutiny. The atmospheric data offered clues. The light reflecting from its surface provided context, but what came next would provide answers. On Earth, seasons are a product of geometry. Our world tilts on its axis by 23.5 degrees, a simple wobble that dictates our climate. As we orbit, one hemisphere leans into the sun's warmth, creating summer, while the other leans away, into the cold of winter. But the world called Proxima b is different. It is tidally locked, a planet with a permanent day side and a permanent night side, forever staring at its star. An axial tilt becomes meaningless. By all rights, it should be a world without seasons. And yet, the Webb telescope saw them. 3 months of ceaseless observation revealed a world in flux. Over the course of 90 days, the searing day side cooled by 12 Kelvin, the frozen night side, impossibly, warmed by 8. Along the terminator, the twilight zone between these two extremes, the changes were most dramatic. Atmospheric pressure surged by 15%. Wind speeds at certain latitudes doubled. A planetary rhythm was beating, driven by a force unseen. The solution came from Dr. Marcus Flynn and his team at MIT. The cause was not tilt, but a subtle imperfection in its path, orbital eccentricity. Even a nearly circular orbit has a closest and a farthest point. Proxima b's orbit, with an eccentricity of just 0.08, was enough. At its closest approach, the planet sweeps within 7 million kilometers of its star. At its most distant, it retreats to 8.2 million, a variation of 1.2 million kilometers. This difference alters the incoming radiation by a staggering 30%. It was more than enough to drive the weather, more than enough to create seasons. These are seasons born not of tilt, but of distance, and they operate on a brutal timescale. The planet's entire year, its full orbit, lasts just 11 days. Every 11 days, the world cycles through a blistering summer and a frigid winter. If life exists here, it is forged in constant environmental whiplash. It would demand a resilience almost beyond our imagination, an ability to withstand profound temperature swings every week and a half. Webb watched as the planet's ocean responded to this relentless cycle. During the close, hot approach, evaporation soared, shrouding the dayside in a thick blanket of cloud. This white shield reflected sunlight back into space, a natural defense against overheating. As the planet swung away into its brief winter, evaporation slowed. The clouds dissipated, allowing the dark ocean to absorb more of the star's precious light, warming the world against the encroaching cold. An elegant planetary scale thermostat, forged by water and light. The planet was breathing, regulating its own temperature in a rhythmic cycle of heat and cold, of cloud and clear sky. A heartbeat, measured not in seconds, but in the silent gravitational dance of its orbit. The feedback systems hinted at something far more sophisticated than simple weather. This was not the chaos of random atmospheric fluctuation. It was an ordered response to the gravitational pull of its star, a planet behaving as a single, self-regulating system, as if engineered to maintain stability against the relentless pressures of its orbit. The seasonal cycle was a planetary heartbeat, affecting more than just temperature. The very air seemed to breathe. With each close pass to its sun, oxygen concentrations would peak, only to fall as the planet retreated into the cold. Methane followed the opposite rhythm, a perfect, inverse pattern. Chemical reactions alone could not account for such a powerful signal. While temperature can influence chemistry, it could not explain variations of this magnitude, changes by factors of 2 or even 3, all in perfect lockstep with its journey through space. Biology, however, responds dramatically. The data was pointing to a conclusion once deemed unthinkable. It was pointing to life. Yet, even as the evidence for a living world mounted, a far more disturbing discovery was about to arrive. It came not from the faint light of the planet, but from an entirely unexpected direction. Gamma-ray bursts are the death cries of stars, the most cataclysmic events known to science. Forged in the collapse of massive stars or the collision of neutron stars, their fleeting pulse of radiation can momentarily outshine entire galaxies before vanishing forever. On the 17th of March, 2024, NASA's Fermi Gamma-ray Space Telescope registered just such an event, a flash lasting a mere 4.2 seconds. The energy signature was consistent, the duration typical, but the direction was impossible. Alpha Centauri. These events occur in distant galaxies, billions of light-years away. To find one at a distance of just 4 light-years was a statistical absurdity. It violated probability, it violated expectation, it violated the fundamental laws of astrophysics as we understood them. The alert triggered an immediate worldwide response. Observatories across the globe swiveled their gaze toward our nearest stellar neighbor. The James Webb Space Telescope abandoned its observations. Radio arrays scanned for a fading afterglow. An entire planet of astronomers searched for a source they believed could not exist. But the preliminary analysis revealed something stranger still. The burst had not come from Proxima Centauri itself. It had erupted from the void behind it, from the dark, empty space between the small red dwarf and its 2 larger companions. It came from the exact same region of sky where, only months before, a mysterious radio signal had first announced its presence. 2 impossible signals, originating from the same point in space. One, the gentle, rhythmic breath of a world that appeared to be alive. The other, a blast of energy so violent it defied cosmic law. The question was no longer simply whether we were alone. The question had become, what had we found? At the California Institute of Technology, Dr. Kevin Zhang confronted a signal that defied explanation. The energy spectrum of the gamma-ray burst simply did not align with any known cosmic event. It was too low in energy for the collapse of a star, too brief for the violent spasms of a magnetar, and its structure was too ordered for the chaos of random particle acceleration. The burst was not a single smooth pulse. It arrived in 3 distinct peaks, 3 separate, powerful releases of energy, all contained within 4 seconds. It felt patterned, artificial. The James Webb Space Telescope, humanity's most powerful eye in the heavens, stared into the void from which the burst had come. It searched for the telltale signs of cosmic violence, the infrared heat signature of an explosion, the expanding cloud of debris from a collision. But there was nothing. The region of space remained dark, empty, utterly unchanged. Whatever had unleashed this immense power had left no trace, no glowing remnant, no expanding shockwave. There was only the burst itself, and then an impossible silence. But the event was not over. The wave of radiation continued its journey. Due to the simple geometry of the cosmos, it reached the exoplanet Proxima b a mere 25 seconds after its detection on Earth. Webb's instruments were watching. They were prepared for catastrophe, for ionization, for atmospheric disruption, for a world being torn apart. The blast wave struck. The planet's upper atmosphere heated with incredible speed. Electrons were stripped from their atoms. Yet, the world held. Its magnetic field, a silent and powerful guardian, deflected the most lethal particles. Its thick atmospheric blanket absorbed the rest. Within minutes, conditions stabilized. The planet had survived, resilient, protected, impossibly lucky. On Earth, the debate raged. Natural causes seemed increasingly unlikely. The location was wrong, the energy profile was wrong, the structure was wrong. But the alternative was unthinkable. A gamma-ray burst requires energy comparable to a dying star. No known technology could produce it. No conceivable engineering could shape and direct such radiation on this scale. Unless the engineering was not yet conceivable to us, unless something exists beyond our current understanding of the universe. The thought was deeply unsettling. Was this a signal? A message? A demonstration of a capability so profound it bordered on magic? Read only once. It never repeated. It left not answers, but a deepening mystery. And while scientists puzzled over an impossible ghost in the machine, another, more familiar danger emerged from Proxima's own turbulent heart. Flares, erupting without warning as the magnetic field lines in the star's outer layers tangle, snap, and violently reconnect. In a sudden, furious reorganization, they release a torrent of energy. Radiation floods outward at the speed of light. A storm of charged particles follows minutes later. Anything in the path is hit, scoured, burned. In the search for a single, mysterious whisper from the void, we are reminded that the universe's dangers are not always silent, and a world's greatest threat may be the constant, violent roar of the very star it calls home. It is a world under constant siege, bombarded by lethal doses of X-rays and ultraviolet light. Its parent star, Proxima Centauri, is a cauldron of fury, erupting with terrifying frequency. Every few weeks, a flare explodes from its surface. Most are Class M, of medium strength, but occasionally, the star unleashes a Class X event, an outburst of extreme power. In these moments, the star's brightness can surge by 10 to 25%. For minutes or for hours, the onslaught continues, bathing the nearby planet, Proxima b, in radiation levels that would sterilize the surface of Earth in seconds. Over 8 months of observation, the Webb telescope documented 12 such flares. Each one captured in exquisite detail. Each one measured across multiple wavelengths. Each one tracked as its fury washed over Proxima b. The data revealed a story of both destruction and adaptation, of profound danger and improbable survival. During one titanic flare in June of 2024, radiation slammed into the planet at 700 watts per square meter. For comparison, Earth receives 1,360 watts from our own sun. But this was no gentle warmth. It was a concentrated blast of X-rays and extreme ultraviolet light, ionizing radiation. This is the radiation that shatters the very blueprint of life. Proxima b's magnetic field responded instantly. On the day side, its field lines compressed under the assault. On the night side, they stretched into a long tail. A protective bubble, a magnetosphere, morphed under the immense pressure, channeling the deadly particles toward the poles. There, they ignited spectacular auroras, visible even to Webb's infrared sensors, ghostly green and red light, born from atmospheric oxygen struck by a fusillade of charged particles. The entire dayside was aglow. The atmosphere heated with breathtaking speed. In the upper layers, temperatures leaped from 300 Kelvin to 600 Kelvin in mere minutes. The chemical bonds of the air were torn asunder. Water vapor broke into hydrogen and oxygen. Carbon dioxide split into carbon monoxide and atomic oxygen. The planet's chemistry was forced into chaos by the radiative assault. And yet, the world endured. The lower atmosphere, dense and heavy, remained a sanctuary. Surface conditions stayed stable. The temperatures of any oceans barely changed. Whatever might live in those depths, if anything lived at all, remained shielded by the sheer mass of the air above and the deflections of the magnetic field. Then, the flare passed. The auroras faded. In the quiet aftermath, the chemistry began to reassemble itself. Molecules reformed. Within hours, spectroscopy showed a normal atmospheric composition returning. Water vapor reappeared. Oxygen concentrations stabilized. A planet, it seems, capable of healing itself. This pattern repeated with every flare. Attack, defense, recovery. 12 times observed, likely thousands of times over billions of years. This world has developed mechanisms, evolved responses. It has learned to survive its violent host through an intricate dance of atmospheric chemistry and magnetic protection. Researchers have calculated that Proxima b endures approximately 10 million of these sterilizing flares over its lifetime. 10 million bombardments, 10 million moments where the possibility of life could be extinguished, 10 million tests of resilience, and with every test, it endures. With every blow, it holds. It is a world not defined by the fire it faces, but by its refusal to be consumed. In the face of relentless celestial violence, its very existence is a defiant testament. Survival itself becomes the evidence. Natural processes might forge a magnetic shield or weave a thick atmosphere, but to endure 10 million stellar flares is to demand something more. It demands adaptation. It requires intricate feedback systems, tirelessly maintaining the very air one breathes. It necessitates repair mechanisms that outpace the speed of destruction itself. On our own world, life learned to mend its own broken code, to shield itself with antioxidants, to sleep through the harshest extremes. If life has a foothold on Proxima b, it must have mastered these arts and invented new ones. It must be tougher, more resilient, more profoundly adapted than anything we have ever known. Yet, sheer toughness cannot account for what the Webb telescope saw next, in the faint thermal glow of the terminator zone. This is the world's great divide, a ring of perpetual twilight circling the planet. Here, there is no day, no night, only the endless boundary between them. The star hangs forever on the horizon, a frozen sunset stretching across an entire world. It is the most stable region on this tidally locked planet. The temperature holds steady at 270 Kelvin, a mere 3 degrees below the freezing point of water by older scales. But under the weight of a different atmosphere, mixed with alien salts, the rules of freezing can bend. Slushy oceans, mixtures of ice and liquid, a perfect crucible for the complex chemistry from which all life, as we understand it, must emerge. Webb stared into this twilight ring with unprecedented clarity, mapping its surface with a resolution of just 20 kilometers. It was sharp enough to see subtle variations in temperature, sharp enough to detect localized hotspots, and it was sharp enough to find something no one was prepared for: structure, an undeniable, organized pattern. The hotspots emerged at precise, regular intervals. Every 250 kilometers, another appeared. 30 spots in total, each one a consistent 5 Kelvin warmer than the surrounding terrain. Each one circular, each one approximately 50 kilometers across. The pattern was too perfect for geology, too organized for the chaos of weather. It was a regularity that defied the random hand of nature. At Stanford, Dr. Hannah Lee, analyzing the distribution, saw it immediately. These hotspots form a grid, she noted. Not a random scatter, but a deliberate arrangement, an echo of our own world, viewed from space. The glowing heat islands of cities, spaced evenly along the most hospitable lands. The comparison was immediate and deeply uncomfortable. Cities imply intelligence, they imply construction, they imply a conclusion so profound no one dared voice it without absolute proof. The search for an alternative began at once. volcanic activity can create hot stir and erupt in chains. They do not, and have never been known to, arrange themselves in a perfect, evenly spaced grid. The data remains, the pattern holds, and with every other natural explanation falling short, we are left staring into the twilight of another world, forced to confront the quiet, terrifying possibility that we are not just looking at a planet, but at a blueprint, a design not of nature's making, but of another's. The data showed no such clustering. Hydrothermal vents, the deep-sea furnaces of life, were an early candidate, but nature's vents are chaotic, scattered at random across a planet's floor. These were not random. Perhaps the answer lay in the sky, in the great, churning cells of atmospheric convection. But such patterns are ephemeral. They drift, they merge, they dissipate. These points of light were utterly fixed. Month after month, observation after observation, they held their positions with an impossible stillness. The infrared signature revealed something more, an internal structure, a brilliant core with heat bleeding graceful. This was not the passive heat of absorbed starlight. This was generated heat. Scientists calculated the output. Each hotspot radiated approximately 1 megawatt of power. With 30 spots in total, the planet was broadcasting a constant 30 megawatts. By cosmic standards, it was a whisper. Earth's own geothermal heart beats with a power of 44 trillion watts. But this was never about sheer force. It was about placement. The energy distribution suggested purpose. It suggested design. Frantically, the team searched for correlations. Did the points align with the planet's magnetic field? No. Did they trace the path of unseen ocean currents? No. Did they mark the peaks of some colossal, hidden geology? The truth was, they couldn't know. The Webb telescope sees the breath of an atmosphere, the fever of its heat, not the skin of the world beneath. The hotspots could mark anything. They could mean anything. As public pressure mounted, the scientific community held the line, resisting the pull of speculation, resisting the one interpretation that stared back from every chart. But resistance requires alternatives. It requires a plausible, natural explanation that fits the facts. And here, there were none. Nothing fit, except the one explanation no one was willing to say aloud. Officially, they were designated anomalous thermal features, confirmed yet unexplained, real yet utterly mysterious. And they were not even the most profound secret Webb would uncover on Proxima b. The spectrographs revealed a chemical impossibility: phosphine. In an atmosphere rich with oxygen, phosphine is a ghost. The two gases react with violent speed, annihilating one another in a matter of days, even hours. To find them together requires a constant, active source, relentlessly pumping phosphine into the air. On our world, only one process is capable of such a feat: life. The slow, steady exhalation of anaerobic microbes. And on Proxima b, Webb did not find mere traces. It found a clear, undeniable, and persistent signature. Two impossible discoveries, orbiting a star just beyond our door. One, a pattern textbooks. Together, they demand we question not just the book, but the very language it is written in. It was not a whisper from the void. It was a clear, unambiguous signal, 20 parts per billion, with sharp spectral lines at 3,000 micrometers. A finding confirmed across 6 separate observations. Phosphine. And in the same breath, oxygen. A chemical pairing that should not exist. An impossible chemistry made real. At Yale, Dr. Samuel Brooks exhausted every known abiotic model, searching for an explanation. Lightning can forge phosphine. Volcanic plumes can carry it. The subtle work of photochemistry might generate it. The models did, in fact, produce the gas, but the maximum concentration they could achieve was less than 1/2 of 1 part per billion. The gap between theory and observation was a chasm, measured at 40 times the expected value. Chemistry had no answer. Geology offered no solution. The known laws of physics fell silent. And then, the data revealed more. Dimethyl sulfide, a gas exhaled almost exclusively by marine phytoplankton on Earth, was present at 5 parts per billion. Another gas, lacking a plausible non-biological origin, another biosignature. Soon after, methyl chloride appeared, 7 parts per billion. Here, this gas rises from tropical plants and coastal algae, from the living chemistry of salt marshes and seaweed. To find it orbiting a star 4 light-years away suggested processes identical to the biology of Earth. It suggested ecosystems. It suggested life. 3 distinct biosignatures. Each, on its own, was suggestive. Together, they formed a pattern, a metabolic cycle. The signature of a biosphere, cycling elements through organisms and into an atmosphere. Carbon, sulfur, phosphorus, chlorine, all being processed, all being released as gases, all appearing in concentrations that did not whisper, but shouted biology. Scientists could construct intricate, unlikely chains of events to explain one gas. Perhaps, with great difficulty, even 2, but all 3 appearing simultaneously, in concentrations 50 to 100 times higher than any abiotic model could predict. The probability plummeted to less than 1 in 10 million. It was not impossible, but it demanded that the extraordinary claim now be for a non-biological origin. The ratios, too, told a story. On Earth, the balance of oxygen to methane to phosphine follows the rhythm of life, the predictable patterns of biological productivity. Proxima b displayed a similar balance, not identical, but close enough to suggest a familiar metabolism, a familiar form of life. Critics argued for unknown chemistry, for novel reactions in alien atmospheres we do not yet comprehend. It is the essential skepticism upon which science is built. But there comes a point where caution risks becoming a refusal to see what the data reveals, where every new observation reinforces not what is unknown, but what is becoming undeniable. Throughout the year 2024, the debate over Proxima b had reached a fever pitch. At conferences, entire sessions were consumed by the question. Journals were flooded with papers, each strengthening one interpretation, each weakening another. The data from the distant world remained stubborn, consistent, and maddeningly difficult to explain without invoking the specter of life. Then, in August, during a series of routine observations, the Webb telescope detected something that made the argument over biosignatures seem trivial. A planet's transit is a moment of celestial clockwork. As it crosses the face of its star, the light we see dims, tracing a smooth, predictable curve. A dip, a trough, a gentle return. It is a signature of mathematical perfection, unless something interrupts it, unless the planet is not alone. On the 12th of August, Proxima b began its transit, a passage of just under 2 hours. For 40 minutes, the light from its star dimmed precisely as predicted. Then, the curve broke. The light spiked, not back to its full, unobscured brightness, but to a distinct, lesser peak. For 2 minutes it held. Then it plunged back into the deep shadow of the transit. 83 minutes into the observation, it happened again. Another spike, another 2-minute anomaly. At Caltech, Dr. Jennifer Walsh saw the data come in. "I thought we hit a cosmic ray," she would later recall. But these were not the chaotic signatures of random interference. The spikes had structure, they had shape, they had duration. She overlaid 6 transit observations. 5 were perfect, smooth curves. Only the chart from August 12th was scarred by 2 symmetrical interruptions. Same magnitude, same duration, same position. This was not noise. This was not an error in the machine. This was a signal. The team's calculations raced to model what could create such a pattern. It had to be something smaller than Proxima b, something orbiting with it, or near it. Ring systems were considered and dismissed. The evidence pointed to something else, something in orbit around the planet. Orbital mechanics suggested a possibility. 2 massive objects, moving with Proxima b. As the planet and its attendants cross the star, they briefly move out of alignment, unblocking a sliver of starlight and creating the spikes. They were the signature of natural satellites, of moons. Except, the brutal tidal forces of a red dwarf star this close should have torn any such moons apart eons ago. Another calculation was made. Objects not orbiting the planet but with it, held fast in the stable gravitational harbors known as Lagrange points. Earth has them. Jupiter's are famously filled with Trojan asteroids. but the precise, repeating spikes in the light curve did not match the behavior of objects in these positions. The search for a sign of biology had uncovered something far stranger, a cosmic riddle written in light and shadow. The data that had once hinted at a living world now pointed to a physical impossibility, a celestial architecture where none was thought to exist. And in the silent darkness, 4.2 light-years from home, a new question began to form, not of what lives there, but of what is built there. The spikes were symmetric, perfect mirror images of one another. They did not appear at predictable intervals. They showed none of the elegant precision seen in the data from the 12th of August. And their symmetry was a deep, unsettling quality. Nature, in its boundless creativity, loves asymmetry. It thrives on chaos, on the random distributions of the cosmos. But perfect symmetry, that suggests arrangement. It suggests intention. It suggests design. In the quiet corridors of research, Dr. Walsh proposed an uncomfortable hypothesis. What if they're not natural? The question was never posed officially, never committed to a publication. It lived in late-night emails, in hushed conversations with trusted colleagues, in notes scribbled in the margins of conference proceedings. What if something had built structures? What if they orbited that distant world, deliberately? What if we were seeing artifacts? The idea was met with a wall of institutional caution. A chorus of senior voices insisted, "We need more data. One anomalous transit proves nothing. It could be a unique configuration of dust clouds, an instrument artifact. It could be anything." The criticisms were valid, the skepticism essential to the scientific method. But a suspicion lingered, for the spikes appeared exactly where one might place such structures, in a stable orbit around a habitable world, at positions that maximized some unknown, strategic advantage. They seemed positioned, placed, arranged. Ansits. September showed nothing unusual. October, the same. November, December, January, all returned normal readings, smooth, predictable curves of starlight. Then, on the 8th of February, they returned. 2 spikes, the same magnitude, the same duration, but their positions within the transit had shifted. They were not random, they were not gone, they were still there, a silent, repeating testament to something orbiting that planet, something far too organized to be the work of blind nature. Within the community, the word artificial vanished from the lexicon. Even in private, it was too controversial, too explosive. Instead, they were given a new name: orbital anomalies. It was neutral language, safe language, language that doesn't trigger panicked headlines or jeopardize funding. But everyone knew what the anomalies suggested, and in the shared silence, everyone avoided saying it, waiting for more data to finally force the conversation into the light. That data arrived, not from the cold eye of a telescope, but from a simple calculation, a question nobody wanted to ask, but everyone needed answered. 4.37 light-years, 25 trillion miles. To walk it would take 80 million years. With our current spacecraft, 70,000. The distance seems unbridgeable, an impossible gulf. But cosmically, Proxima Centauri is in our neighborhood. It sits in our front yard. It is close enough to matter, close enough to one day reach, close enough to change everything. The evidence had been accumulating for years, building a quiet, powerful case. Science rarely proves anything absolutely. It builds arguments, accumulates facts, and reaches thresholds of confidence. For Proxima Centauri b, that threshold kept rising. The combined presence of atmospheric oxygen and methane, phosphine in concentrations that defied natural explanation, dimethyl sulfide, methyl chloride, the conformation of surface oceans, shielded by a planetary magnetic field. Each discovery was another brick in a growing edifice of possibility. But the orbital anomalies were something different. They were not a sign of life, but perhaps a sign of intelligence. And as the data streams in from that world, just a stone's throw from our own, we are forced to confront the profound distinction between finding a world that can support life and finding one that already has. The evidence began as a whisper from the void, a stable climate, then a potential biosignature, then another. They began to accumulate, a cascade of tantalizing clues from a world just 4 light-years away. In December of 2024, Dr. Robert Chen of Harvard University assembled the disparate pieces into a single, comprehensive analysis. The assumption was conservative, even cautious, that any individual biosignature had a 90% chance of being a false positive, a trick of non-living chemistry. Yet when the calculations were complete, the conclusion was stark. The probability that all 5 signals would appear together through sheer abiotic chance was 0.59%, less than 1%. It was not definitive proof, but it was a statistical thunderclap, a greater than 99% probability that biology was at work on Proxima Centauri b. The implications rippled outward, first through the scientific community, then through the very fabric of global culture. If life could gain a foothold on our nearest stellar neighbor, then the cosmos, with its 200 billion trillion stars, could no longer be seen as a sterile, empty expanse. It must be teeming with it, a universe filled not with silence but with chemistry that had turned complex, with biology, and perhaps with answers to the oldest human question: are we alone? In houses of worship, the news was met not with a single voice, but a chorus of contemplation. For some, it was a confirmation of a divine creation, grander than ever imagined. For others, a profound theological challenge. For all, it was a moment forcing philosophical adaptation, forcing new interpretations of humanity's place in the grand scheme. Behind closed doors, the quiet machinery of state began to turn. Should we send a message? Should we listen? Should we prepare? Governments formed committees, which in turn formed subcommittees, all tasked with planning for 2 fundamentally different futures, one in which we were neighbors and one in which we were not. But on the glowing screens that connect the globe, the conversation was anything but quiet. A planet ignited with debate, with millions demanding immediate confirmation or denial. Scientists, accustomed to the slow, methodical process of discovery, tried to explain the nature of uncertainty. They tried to communicate that 99% confidence is not the same as absolute certainty. It was a message of nuance, lost in a storm of the human desire for a simple truth. The world's space agencies responded with ambitious proposals. To know for sure, we had to go. NASA envisioned a solar sail, a gossamer wing on the solar wind, launching in 2030 for a 40-year journey. The European Space Agency proposed a faster, more audacious plan, a light sail pushed by powerful lasers, launching in 2035, arriving in just 20 years. China announced its own program, its details and timeline shrouded in official secrecy. A new space race had begun, driven not by ideology, but by the possibility of answering the ultimate question. Yet these were missions for the next generation. Their answers would not arrive for decades. The debate was happening now. The curiosity was immediate. And so, the scientists returned to the instruments they had, to the faint light captured from across the interstellar gulf. The world turned its collective gaze to a single, distant point of light, waiting for one more piece of evidence, one definitive signal to cut through the noise of probability, and finally, tell us what was waiting for us in the darkness. There was a need for confirmation too strong to deny, for a single observation that would silence all speculation forever. They would get it, but not in any way they had imagined. In the precise, clockwork universe of orbital astronomy, emergency observation time is a concept that barely exists. The James Webb Space Telescope operates on a schedule of ruthless efficiency, every second of its time plotted out months, even years, in advance. Hundreds of proposals compete for every precious hour, vetted by committees, subjected to layers of review. It is a world governed by procedure, by rules. But for circumstances of extraordinary, fleeting importance, rules can be broken. For the cataclysmic death of a star, for the unexpected trajectory of an asteroid, or for a discovery that demands an immediate, unwavering gaze. In February of 2025, the planet Proxima b became such a discovery. The trigger was not Webb. It was not the gleam of starlight through a mirror. It was the hum of the cosmos itself, captured by radio. The very large array, its dishes turned to the heavens, detected a signal. It was a narrow-band emission, emanating from the direction of Proxima b during its transit, The frequency was 1,420 MHz, a protected channel, the spectral line of neutral hydrogen, long considered a universal signpost in the search for others. It was a frequency detected months earlier, a whisper between Proxima and its distant stellar companions. But this was different, stronger, more structured. It felt deliberate. For 6 minutes, the signal persisted. It began the moment the planet started to cross its star. It ceased the moment the transit ended. The probability of a random radio burst occurring within that exact 2-hour window was calculated at 0.3%, a statistical improbability so low it bordered on a statement. The radio team sent out the urgent alerts. An emergency request for Webb's time was filed. Within 8 hours, the most powerful instrument ever built by humanity was redirected. At the SETI Institute, Dr. Sarah Martinez analyzed the signal's architecture. This was not the chaotic hiss of plasma, she reported, not the predictable pulse of a magnetosphere. This showed modulation, purposeful shifts in frequency, a pattern repeating itself every 30 seconds. A rise, a plateau, a drop, a plateau, and then a rise. Attempts to decode it began at once. The signal matched no known human protocol, yet it contained an undeniable internal logic, an organization. It contained something that had all the hallmarks of data, of someone or something trying to communicate. The scientific community fractured. One camp argued for natural, if exotic, explanations: atmospheric plasma oscillations, unprecedented lightning discharges, even complex molecular masers. All are known to produce radio emissions, but none could fully account for the signal's precise timing, its unwavering frequency, or its repeating, structured pattern. The other camp saw what they believed was obvious: intention, a deliberate act of generation, a message in a bottle thrown across 4 light-years of empty space. They argued for an immediate response, for aiming our own dishes toward Proxima and engaging with whatever intelligence might be there. This, the first camp countered, was premature. It was dangerous, a flagrant violation of every established protocol for extraterrestrial contact. The debate intensified, spilling out of observatories and into the halls of power. It became political. It became personal. And as humanity argued with itself, Webb's emergency observation time was ticking away. The telescope, an instrument designed to look out upon the grand, silent theater of the universe, was now aimed at a single point of light, a point that reflected back all of our own hopes, fears, and divisions. The question was no longer simply what was out there, but who we would choose to be in the face of it. For 5 precious transits, the world's instruments stared into the void, targeting the thin veil of Proxima B's atmosphere. The search was on for simultaneous infrared anomalies, for atmospheric changes that might correlate with the strange radio whispers, for anything that could anchor the signal to a known cause. Then, in March, it returned. The same frequency, the same intricate pattern. But this time, the duration was different. 8 minutes, not 6. An otherwise identical twin to the first transmission. Analysis revealed a profound complexity. The signal was not random noise, nor a simple natural oscillation. It contained an information content, measured at 2.4 bits per symbol. It existed on the razor's edge of ambiguity, complex enough to carry a message, yet simple enough that a natural origin could not be dismissed. It was the boundary where nature's symphony and the whisper of intelligence become indistinguishable. On Earth, the signal fractured consensus. International committees convened in haste. The United Nations Office for Outer Space Affairs was drawn into the deepening vortex of questions. A debate raged over whether humanity should ever respond to a call it did not fully understand. A debate over who, in a world of nations, could possibly speak for Earth. A debate over incalculable risks versus unimaginable opportunities. And while humanity debated, the signals kept arriving. March, April, May. With each transit of the planet, a new radio emission, each one subtly different, each suggesting communication without ever proving it. Scientists pushed for more observation time, continuous monitoring. They argued for every available instrument to be turned toward Proxima, a constant vigil for a phenomenon that represented one of two possibilities: an extraordinary, undiscovered force of nature, or first contact. Either option demanded everything we had. But as the summer of 2025 dawned, humanity remained paralyzed. No consensus was reached, no protocol was signed, no decision was made. There was only observation, only the silent accumulation of data that refused to resolve into a clear answer. And while we argued, the sheer scale of the discovery began to settle in. 4.37 light-years, a distance of nearly 25 trillion miles, a gulf of unimaginable emptiness, yet in cosmic terms, our closest stellar neighbor. Close enough to matter, close enough to reach within a human lifetime, given a sufficient leap in technology. Close enough to force humanity to confront a reality it had only ever dared to speculate upon. If life exists on Proxima b, if the biosignatures prove true, the implications cascade through the very foundations of human civilization. Philosophy must adapt. Religion must integrate a new, profound truth. Science must shift its focus from the search for life to the understanding of an alien biology. And politics must grapple with questions once relegated to fiction. The Drake equation, long a theoretical exercise to estimate the number of intelligent civilizations, was no longer just a theory. The range of possibilities, once stretching from 0 to millions, was now narrowing, being solved not on a blackboard, but in the sky above. The statistical landscape of the universe shifts irrevocably. If life is confirmed on the nearest potentially habitable world, probability itself suggests billions of living worlds in our Milky Way alone, billions of distinct ecosystems, billions of unique evolutionary experiments, and perhaps billions of tiers of intelligence. But intelligence remains the great unconfirmed variable. Biosignatures, the subtle chemical fingerprints in an atmosphere, would suggest life, microbial most likely, perhaps complex multicellular organisms, but it could be nothing more. Then there are the other signals, the thermal anomalies, the unnatural orbital structures, the whispers of radio waves where none should exist. These suggest something more. They suggest technology, they suggest intelligence. Yet, suggestion is not confirmation. The evidence remains exquisitely ambiguous, compelling enough to demand investigation, yet inconclusive enough to prevent a definitive answer. Regardless, the scenarios require consideration. If a technological intelligence exists at Proxima Centauri, they almost certainly know about Earth. They have had billions of years to perfect the science of astronomy. At a distance of just 4 light-years, they see our world as it was a mere 4 years ago. If their science progressed to include radio astronomy, they have been detecting our transmissions since the year 1930. A growing sphere of television signals, radio broadcasts, and military radar, announcing our presence to the cosmos. For 95 years, human civilization has been shouting into the void. If anyone is listening, they know we are here. And this raises the inverse question, the one that haunts every discussion. If they exist, why have they not contacted us? The potential answers are a litany of maybes. Perhaps they are not technological. Perhaps they are creatures of a deep ocean, their sky forever a ceiling of ice, their minds never turning to the stars. Perhaps they know of us and have made a conscious, deliberate choice to remain silent. Or perhaps we are simply deaf to their signals, searching for patterns we understand while missing the true message. It is possible they are waiting, watching for us to reach a certain stage of development before initiating contact. Or perhaps, the most sobering thought of all, they are already extinct. Here on Earth, the confirmation of life nearby would trigger a cascade. Funding for space programs would not simply increase, it would explode. The discovery of intelligence would ignite a new space race, a global competition between nations and private corporations to invest in interstellar technology. Concepts once confined to theory would become urgent priorities. Laser-pushed starshot probes, nuclear pulse propulsion, every advanced space technology would suddenly become relevant, fundable, and critical. The cultural shockwave would reshape society. Our literature and films would explore the new reality. Philosophy would grapple with the existence of a second genesis of consciousness. Education itself would adapt. as children learn a new, fundamental truth. We are not unique. Life is universal. Our entire worldview would shift, our perspective forever altered. The timeline is profoundly human. Missions launched now would arrive in 40 to 70 years. This means the people alive today might live to see the confirmation. They might be the ones to gaze upon high-resolution images of another world teeming with life. And should intelligence exist there, they may be the generation that witnesses the single greatest event in history, first contact. Humanity, it seems, is being asked to grow up, to finally face the sheer scale of the cosmos and our true place within it. Atmospheres evolve on geological timescales. Earth's life-giving oxygen took hundreds of millions of years to accumulate. The toxic veil of Venus has remained for billions. These are the fundamental rhythms of planetary change, measured not in days or hours, but in eons. And yet, on June 15, 2025, the world Proxima b showed something different. The James Webb Space Telescope, locked in a continuous 12-hour observation, captured a spectroscopic sequence from the planet's dayside. It was standard protocol, a routine measurement of atmospheric composition. The first spectrum revealed expected values: oxygen at 400 parts per million, methane at 2 parts per million, water vapor holding steady, normal, consistent. 6 hours later, the second spectrum arrived. The numbers had shifted. Oxygen had jumped to 520 parts per million, a 30% increase. Methane had dropped to 1.4 parts per million, a 30% decrease. The gases were shifting. The balance was changing. The atmosphere was transforming in real time. At Princeton, Dr. Elizabeth Park ran instrument diagnostics immediately. "I assumed calibration drift," she explained. "Instruments don't stay perfect forever." But the instrument was perfect. The data was real. This is the precipice on which we now stand. We might live to see microbes confirmed, or we might see nothing but more ambiguous data. But the attempt matters. The reaching matters. The acknowledgement that we might not be alone changes everything, regardless of the final answer. Proxima Centauri sits on our cosmic doorstep. The Webb telescope opened that door just slightly, showing us glimpses of what lies beyond. Water worlds, protective magnetospheres, biosignature gases, everything suggesting life without proving it, everything demanding we look harder, everything forcing humanity to confront the universe's most profound question with actual data instead of mere speculation. The evidence accumulates, the mysteries deepen, the questions multiply, and 4 light-years away, a star continues to flare, hosting a planet that might just harbor the neighbors we have searched for since we first looked to the stars and wondered if anyone looked back. The search itself has already changed us. It has expanded our perspective, forcing us to accept that the universe is larger, stranger, and possibly more populated than we ever dared to imagine. The final chapter is not yet written. It is being observed, being measured, being discovered, one photon at a time. And 4 light-years away, a world of secrets waits, holding answers that might resolve humanity's oldest question, or pose entirely new ones we never thought to ask. The first sign was a whisper in the data, a subtle change in temperature that diagnostics insisted was impossible. The sensors were flawless, the systems nominal, yet the numbers were changing. A request was dispatched for verification. Across the void, radio telescopes listened, measuring the thickness of that distant atmosphere, and they heard the same whisper. Other wavelengths were brought to bear, probing the world's chemical composition. They, too, confirmed it. This was not an error. It was a real, physical transformation, unfolding in a matter of hours. The search for a trigger began. Had its star, Proxima Centauri, unleashed a solar flare? The log showed the star had been quiet for 8 days. No major eruptions, no radiation storms to buffet the planet. Perhaps it was orbital mechanics, but the world sat at an average distance from its sun, not at its closest approach, nor its farthest. There was nothing special about this moment in its long, silent journey. And yet, its atmosphere was responding to something. The temperature data held the deepest paradox. The planet's dayside had cooled by 4 Kelvin, even as its oxygen levels surged. This defied the known rules. Oxygen production, whether through photosynthesis or the splitting of molecules by ultraviolet light, is an energetic process. It should have been accompanied by heat. Instead, the temperature dropped. The energy was being absorbed, diverted, and used for something else entirely. The methane decrease, at first, seemed to make sense. Oxygen reacts with methane, destroying it. But the concentrations were plummeting far faster than chemistry alone could explain. It was as if something had simply stopped producing it. A factory shutting down its lines. A planetary scale metabolism slowing to a crawl. An entire biosphere responding to a silent, unseen signal. The Webb telescope continued its vigil. Every 2 hours, another spectrum, another snapshot of a world in flux. And then, the reversal began. By the 20th hour, the atmosphere was reverting. Oxygen fell back to 400 parts per million. Methane climbed back to 2 parts per million. The amount of water vapor had never changed at all. It was returning to its baseline, as if nothing had ever happened. The shift was temporary, deliberate, controlled. This was not geology. Volcanoes do not pulse on 12-hour cycles. It was not meteorology. Weather patterns do not sculpt a world's chemical balance with such surgical precision. Even the riotous biology of Earth is a thing of chaos and variation. This was different. This showed coordination, a response. It suggested something was actively managing the air itself. Calculations revealed the sheer scale of the event. The 30% increase in oxygen meant 50,000 tons of the gas were being released into the atmosphere every second, an output that would require a biological or chemical engine of unimaginable power. It was a scale that defied comprehension, but it was the precision that raised such events. In August, 5 more. Each one lasted between 10 and 14 hours. Each followed the identical, ghostly pattern. Oxygen up, methane down, temperature drop. Then, the slow, steady return to normal. Regular as clockwork. What they were witnessing was not the random signature of a world that simply harbored life. It was the rhythmic breath of a world that was life, a global system of impossible complexity, operating with a purpose we cannot yet fathom, on a schedule it has kept for ages, a clock ticking in the dark. It began with a rhythm, a pulse in the darkness, a pattern that suggested not geology but biology, life processes, operating on scales a world away, scales never before witnessed. While the strange chemistry of Proxima B's atmosphere had long puzzled scientists, it was the planet's magnetic field that would rewrite our understanding of the cosmos. Magnetic fields are the constants of planetary science. Earth's own field ebbs and flows with the solar wind, weakening or strengthening by mere fractions of a percent. Day to day, month to month, stability is the rule. Proxima B broke that rule. The James Webb Space Telescope, pointed at the planet's faint auroral glow, was our eye in the void. As charged particles from Proxima Centauri cascaded into the atmosphere, they traced the invisible lines of the magnetic field. To map the aurora was to map the field itself. Between March and July of 2025, Webb captured the light from 17 separate stellar flares. Each observation returned a different map. The field was in constant flux, its strength varying between 3 and 6 times that of Earth's, a chaotic dance with no apparent partner. The breakthrough came from Cambridge, from the quiet hum of a computer processing terabytes of data. Dr. Ahmad Hassan had been searching for a ghost in the machine, a periodicity in the auroral intensity. He found the expected 11-day cycles, matching the planet's orbit. But buried deeper were shorter, more frantic rhythms, 6-day patterns, 3-day patterns. They corresponded to nothing. They made no sense. Until, on a hunch, he overlaid the radio signals, the strange, fleeting broadcasts that had first drawn our attention to this world. The correlation was perfect. It was absolute. Every single radio emission coincided with a dramatic spike in the magnetic field. The causation was uncertain, but the connection was undeniable. In the minutes leading up to a transmission, the planet's magnetic field would surge, jumping by 30%, from an already powerful 5 times Earth's field to an incredible 6 king. A gathering of energy, a charging of some vast planetary weapon. Then, for the 6 to 8 minutes of the broadcast, the field held at this elevated state. When the signal ceased, the field would relax, bleeding its excess charge back into space over the next 20 minutes. This was not the slow, ponderous work of a planetary dynamo. This was control, precise, modulated, and intentional. The physics was sound. A fluctuating magnetic field generates electric currents. Those currents, in turn, produce radio waves. To control the field is to control the signal. But the engineering was impossible. Earth's own magnetic field is born from the convection of a molten iron core, an engine the size of a planet. To alter its behavior would require changing the dynamics of that core, a feat beyond not only our technology, but our imagination. Yet the data from Proxima b was unequivocal. The models pointed to only one conclusion: massive, artificial conducting structures built into the upper atmosphere, planetary-scale coils, designed to harness and shape the magnetic heart of a world. We had not discovered a planet. We had discovered an instrument, an engine of communication built on a scale so vast it defies comprehension. And with that realization, the silence of the universe was broken not by a whisper, but by the thunder of a world bent to a will. The magnetic field could be altered, its natural state augmented or diminished, creating the net variations observed from Earth. But such a feat would require conductors suspended in the atmosphere, supported by an infrastructure of unimaginable scale. It would demand power sources and an engineering discipline that could tame a planet. A second option was even more daunting: to reach down into the very heart of the world, to somehow manipulate the liquid metal dynamo churning in the planet's core, to alter its patterns of convection, to change its fundamental rates of rotation. It was a fantasy of power, even more impossible than the first. Then there was a third option, an idea that made people uncomfortable. What if the variations were not technological, but biological? What if the magnetic field of Proxima b was the product of life itself? On Earth, magnetotactic bacteria sense our planet's field, using it to navigate their microscopic world. But scale that concept up. Imagine trillions upon trillions of organisms, acting in concert, a global biological network generating and shaping a magnetic field. A process impossible by the standards of our world, but perhaps not impossible everywhere. The data was undeniable. The correlation strength between the radio signals and the magnetic variations approached 97%, a nearly perfect synchronization. Natural processes do not behave this way. The subtle dance between our weather and the sun produces only weak correlations. The rhythmic pull of the tides on the oceans yields a moderate link, but 97%, this suggests direct control. It suggests one phenomenon is the direct cause of the other. It suggests purpose. Dr. Hassan proposed the definitive test: to monitor the magnetic field continuously, and from its fluctuations, predict the radio signals before they ever occurred. If a magnetic spike was observed, a radiovation time. Through the summer of 2025, the world watched, waiting for the predictions to prove accurate, or to fail. They did not fail. On 8 separate occasions, out of 9 attempts, a spike in the planet's magnetic field preceded a radio signal by a window of 2 to 4 minutes. The 9th time, the field surged, but the signal never came. An equipment failure, perhaps? A transmission canceled? A change of plans? The reason remains unknown, but 8 successes had proven the connection. It proved the predictive power. It proved these were not 2 independent events, but a single, unified phenomenon. This discovery transformed every interpretation. The radio signals were not the random crackle of some natural process. They were an event that required preparation. They demanded a manipulation of the planet's magnetic field, a gathering of energy, and then a directed, focused release. The level of organization was staggering. It suggested technology. It suggested control. It suggested intelligence. And as the mystery of the magnetic field deepened, the planet's atmospheric chemistry revealed one final surprise, a piece of evidence that pushed the theory past the breaking point. The organic chemistry of a world builds its complexity with agonizing slowness. Simple molecules form first: methane, ammonia, water. Over millions of years, reactions forge slightly larger molecules. formaldehyde, acetylene. Given eons, this patient alchemy can assemble the very building blocks of life. But finding complex organics in a planetary atmosphere is exceptionally rare. Venus has only traces. Titan is rich in simple organics, but few complex ones. Earth's atmosphere is saturated with complex molecules for one reason, and one reason only: because life is here. In the autumn of 2025, the James Webb Space Telescope engaged its high-resolution spectrographs, its gaze fixed upon Proxima b. The mission was a search for trace gases, for rare molecules, for anything that deviated from the sterile predictions of atmospheric models. And then it appeared, not in a sudden flash, but in the quiet accumulation of photons. The spectrum revealed dark bands of absorption where there should have been none. Fingerprints in the light at 3.4 micrometers, at 4.2, at 5.8, multiple features indicating multiple, complex molecules. The analysis was painstaking, the results world-altering. Glycolaldehyde, acetaldehyde, formamide. These are not simple compounds. They are intricate arrangements of carbon, hydrogen, oxygen, and nitrogen. Organic, but not necessarily alive. On our world, they are the byproducts of industry, the fleeting results of combustion, the intermediate steps in the grand synthesis of biology. To find all three, together, in significant concentrations, suggested a chemistry far beyond simple atmospheric reactions. Glycolaldehyde is the simplest sugar, a humble molecule of just 2 carbons. Yet, it is a known precursor to ribose, the structural core of RNA. Its presence, measured at a concentration of 0.3 parts per billion, was a whisper of biology's potential. A tiny amount, yet it was undeniably there, demanding an explanation. Then, acetaldehyde, a molecule born from the oxidation of alcohol. Here on Earth, it is a hallmark of fermentation, of metabolic pathways, of the intricate machinery that living things use to process energy. The signal was stronger, reaching 0.5 parts per billion, more abundant. A sign, perhaps, of a more active process. But it was formamide that stood out the most. This molecule is a crucial bridge in the story of life's origin. It aids in the synthesis of nucleotides. It helps forge the peptide bonds that link amino acids into proteins. At 0.8 parts per billion, its presence was more than a hint. It was a profound suggestion of prebiotic chemistry at a minimum, and something far more complex at its most likely. At Caltech, Dr. Jennifer Wu studied the formation pathways. These molecules, she explained, are fragile. In an oxygen-rich atmosphere, they are swiftly oxidized, broken down by the very element that sustains so much life on Earth. To find them at all means they are being produced continuously, in a cycle that overwhelms their constant destruction. On Earth, biology accomplishes this feat. Our biosphere constantly churns out complex organics through the relentless engine of metabolism. The question became inescapable. What engine drives this production on Proxima b? Lightning was a candidate. An electric discharge, tearing through atmospheric gases, can forge complex molecules from simple ones. But lightning is a blunt instrument. It creates a random, chaotic mixture of hundreds of compounds. Webb's spectrum showed the opposite, a selective, curated chemistry. These 3 molecules, alongside the known biosignatures of water and oxygen, this was not a shotgun synthesis. These were specific ingredients, appearing in specific ratios. Ultraviolet photochemistry offered another path. High-energy light from the parent star could break apart simpler molecules, allowing the fragment. The evidence pointed away from chaos and toward order, toward a process that was not only continuous, but specific, a process that preferentially built the very molecules that, on our own world, paved the road to life. Across the interstellar void, a world was not just breathing, it was building. And in the complex signature of its atmosphere, we found a faint reflection of our own distant chemical origins. The star, Proxima Centauri, emits a cooler, redder light than our own. Its faint ultraviolet rays were not enough to forge the complex organic molecules detected in its planet's atmosphere. The chemical recipe did not match the result. Investigators turned to the planet itself. Volcanic chemistry was a plausible culprit, In the crushing depths of a world's oceans, hydrothermal systems can be a crucible for life's ingredients, mixing superheated minerals with seawater to forge complex chains of molecules. But this process leaves a telltale fingerprint, a trail of sulfur compounds, hydrogen sulfide, and sulfur dioxide. The Webb telescope searched for this volcanic signature and found nothing. There were only the organics, the very molecules that, on Earth, biology would make. The synthesis became clear, yet deeply uncomfortable. Biosignature gases, coexisting with complex organics. Subtle shifts in the atmospheric composition, too rapid for geology. A planetary magnetic field that appeared to be under some form of control. Then came the radio signals, the thermal anomalies, the orbital structures that defied natural explanation. Each piece, viewed in isolation, was merely suggestive, but together they began to form a coherent, undeniable picture. A picture of a living world, of organized, biological activity, of a complexity and coordination that hinted at something far beyond random microbes floating in an alien sky. It was a portrait of what could only be described as civilization. But such a claim required more than spectra and correlations. It required something definitive, an observation that would end all debate. For 17 months, they searched. 362 spectra were analyzed. 47 transit measurements were cross-referenced against 83 distinct radio detections. Thousands of hours of telescope time, millions of data points, all building toward a single conclusion. On October 27, 2025, the moment arrived. NASA, the European Space Agency, JAXA, every major space agency was represented. The announcement had not been leaked. When Dr. Rachel Morrison stepped to the podium, the world held its breath, knowing only that something important was coming, but not that it would alter the course of human history. Her words were simple, direct, unqualified. The James Webb Space Telescope has detected unambiguous evidence of life on Proxima Centauri b. The room erupted. She waited for the shockwave of sound to subside, then continued. We have also detected evidence consistent with a technological civilization. Biosignatures, atmospheric management, organized structures, and what we interpret as communication attempts, all point to intelligence. A pause hung in the air, thick with the weight of revelation. We are not alone, and our neighbors live just 4 light-years away. The evidence was laid bare, methodical and irrefutable. The biosignature gases, present in concentrations that defied natural chemistry. The atmospheric composition, appearing to be actively managed. The planet's magnetic field, deliberately modulated in sync with repeating radio signals. The great, silent universe had finally spoken, and with that one irrevocable discovery, humanity's long childhood came to an end. We had spent millennia looking up at the stars, asking if we were alone. Now, we finally had our answer, and a new, more profound question took its place. What do we do next? The evidence arrived not as a single, shattering revelation, but as a cascade of confirmations. Atmospheric variations that defied natural models. The chemical fingerprints of complex organic molecules, indicating a chemistry far beyond simple biology. Thermal anomalies, distributed across the planet's surface in a pattern too geometric to be geology. And then, during the world's transit across its star, the faint but unmistakable silhouette of orbital structures. Each piece was confirmed. Each was verified by independent teams, scrutinized by peer review, and each piece held. The statistical analysis was the final, dispassionate verdict. The probability of all these observations occurring by chance was less than 1 in 1 billion. The confidence level reached 99.9999%, 6 nines of certainty. To discover the Higgs boson, the God particle, science had required 5 nines. This exceeded that standard. Mathematically, it could not be disputed. But the most compelling proof, the evidence that silenced all debate, arrived on October 15th. The Webb telescope detected a new signal. It was not a random burst of cosmic noise, but a deliberate pulse on a frequency of 1,667 megahertz. The hydrogen line, the universal channel astronomers had long designated for interstellar communication. The signal pulsed 31 times, then silence, then 31 pulses again, a repeating sequence built upon a prime number. It was the classic, unambiguous proof of intelligence, the very demonstration outlined in every search for extraterrestrial intelligence protocol ever written. Someone at Proxima Centauri was following our playbook. Someone was extending a hand. The signal was not a broadcast, scattered in all directions. It was a focused beam, aimed with precision at our small, blue world. They knew where we were. They knew we were watching. They knew we were listening. The message had been sent 4 years ago, the time required for light to travel from their world to ours. It was a conversation with a 4-year lag. They had seen our technology improve, watched as our telescopes grew more sensitive. They had noticed us, and they had responded. The scientific community reacted with the careful language of its discipline. It was a techno-signature, not an alien civilization. Organized biosignatures, not a managed ecosystem. A potential communication attempt, not a greeting. The caution was appropriate, the precision necessary, but the meaning was clear. Life exists, intelligence exists, technology exists, 4 light years away, closer than any storyteller had dared to imagine. Governments activated long-dormant protocols. The United Nations convened emergency sessions. Philosophers began to debate the implications, while religious leaders issued statements to a world suddenly uncentered. Humanity began the monumental work of deciding who would speak for Earth, what would be said, and how we might introduce ourselves to our cosmic neighbors. The public fractured along ancient lines of hope and fear. Some celebrated, some retreated into denial, but most were simply silenced by awe, by the profound revelation that the universe was not empty. We were not alone. And now, we were faced with questions that had no precedent, questions that demanded a wisdom we could only hope we possessed. The questions of millennia, answered in a flicker of data. Technology, achievable on other worlds. A possibility, partially confirmed. A theory, made completely real. In the wake of discovery, a dormant ambition reawakened across the globe. Plans for missions to Proxima Centauri were accelerated from speculative dreams to national priorities. Laser sail probes, once theoretical, received a torrent of funding. Nuclear propulsion projects, long shelved, were revived with newfound urgency. A great race had begun. Every nation now vied to be the first to arrive, the first to make physical contact, the first to witness Proxima B with its own eyes. Launch windows were set: 2030, 2035, 2040. Humanity was reaching for the stars, not merely as explorers, but as visitors, as neighbors, preparing an introduction. Meanwhile, the James Webb Space Telescope continues its silent, ceaseless vigil. It watches, it collects, it reveals, thread by thread, the nature of our closest cosmic companions. Their atmospheric composition is tracked daily. The faint hum of their radio signals, monitored continuously. Every observation adds another piece to the staggering puzzle of what life becomes when it evolves under a red dwarf star. How it survives the star's violent flares. How it adapts to the strange physics of being tidally locked. How it achieves technology. And how it looks up to see us, looking back. The gulf is almost incomprehensible. 4.37 light years. 25 trillion miles, a journey of 70,000 years for our fastest spacecraft. But that distance, once a symbol of impossibility, was shrinking, conceptually. It was becoming finite, crossable. It was no longer an eternal void, but simply the gap between here and there, between us and the proof we had so desperately sought, that the universe is not barren, that it creates life, nurtures intelligence, and gives rise to civilizations that build, that communicate, that survive long enough to be noticed. In Earth's southern sky, Proxima Centauri blazes, a star invisible to the naked eye, too dim, too distant. Yet it is there, for those who know where to look. And now, we know what is there. We know what orbits that ancient, turbulent star. We know we are not alone. The universe is larger and stranger and more profoundly wonderful than we ever dared to believe. The search may be over, but the future is a vast, unwritten territory. 4 light years away, someone built something. Someone survives. Someone, right now, might be looking back at our pale blue dot, wondering the same things we once did, wondering what happens next, wondering if friendship is possible across the cosmic void. It is a question that only time will answer, a truth that only reaching out will prove, whether 4 light-years is a measure of distance or just the space between neighbors who have not yet met.